se ve aquí, ¿eh?
O sea, es que te lo tengo que quitar desde allí.
Ah, bueno, gracias. Por favor. ¿Podemos empezar? Sí, claro. So, bueno, welcome back to the meeting. We will not start the workshop, boost the understanding of the Mediterranean for adaptation to climate change and extreme events. We are 15 minutes late, but we will start with the observations working group. And to begin, we will have a lecture from Mr. Sanino, if he wants to come. Yeah. On a changing Mediterranean current state and future projections. And you have 30 minutes, not more.
I
will be there.
I have my clock. So, thank you for the invitation. Thank you, Vanessa, for inviting me. And I will give you a very, very simple presentation about the climate status, let's say, of our planet and what is happening in the Mediterranean and what we are doing. I mean, in terms of scientific community to produce the best, let's say, climate projection for the Mediterranean Sea. So most of the slides are very common for you, for sure, like this one. This is just the temperature starting from 1850 now, so there's, of course, an increase, and we know that there is an increase. And for the first time, actually, this increase was something, let's say, different, starting from July 2023 and up to June 2024. Actually, the temperature for the first time for the human being was higher than 1.5 degree. I mean, this is just an average value of the entire planet. This is for the first time. And this is just a threshold. If you remember, the threshold that was, put in place during the COP21. They said, okay, we have to do our effort, we have to do as much as possible to stay below 1.5. Of course, we are not more below 1.5. And this is what happened actually in our planet during the same period. So where you see the reddish part of the planet means that we had extreme values for the temperature. And you see most parts of the planet experience very extreme value for the temperature. What about the Mediterranean? This was for the Mediterranean, and again, the Mediterranean experienced a very, 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 let's say, hot period during 2023-2024. And maybe, we don't know exactly, but we can speculate on this, saying that, for example, during the same period, we had one of the most, let's say, dangerous, but also disruptive medications in the Mediterranean. Maybe all of you remember the storm Daniel that hit actually the north of Libya, making more than 5,000, let's say, 5,000 died during this very tremendous, let's say, we can call medications. So we don't know exactly how this was correlated, but I mean, this is a fact that during this very extreme higher temperature, we experienced one of the worst medications in the Mediterranean. So, and this is what happened in Derna after the passage of this storm. So we had more than 5,000 confirmed dead. Actually, this was 4,700 was an old estimation. The new estimation are more than 5,000 dead confirmed after the passage of the storm Daniel. But during the same period, so 2003, 2024, even our glaciers, over the Alps, we just lose about 10% of our glaciers just in 1 year. So we can say that 2023, 2024 is a sort of climate stress for the test stress for the entire planet and also for the Mediterranean. So what happens when we will be, constantly above 1.5 degrees? So this is just to give you a very, let's say, simple information about extreme events that hit the Mediterranean area. Of course, temperature is just one indicator, but we have more than one indicator. One is the CO2 concentration, and as you know, the concentration is the highest in the last 2 million of years. This is the actual CO2 concentration, and we are, exceeded at global level 420 ppm in 2004, actually, in average for the entire 2024. And as maybe you know, such information comes from 129 stations all around the world. That are, just collecting information about the CO2 concentration in the atmosphere. And among these stations, there is also one station in the middle of the Mediterranean Sea, that is in Lampedusa, that is a station that is just operated by ENEA, the institution where I work, and we have a station just in the middle of the island doing the CO2 measurements. And of course, our data are exactly the same that are collected also in the middle of the Pacific or the ocean, Indian Ocean, and so on. And this is the situation. We are, very far from in terms of CO2 concentration. If we look back in time, this is just a plot showing the CO2 concentration starting 800,000 years ago, actually. So from this point of view, we are the first human being that are just breathing an atmosphere that is completely different from the past. But again, CO2 is another indicator, but also the Arctic Ocean. So if we look at the Arctic Ocean, it's the lowest level in the last 1,000 years. This is the decline of the extent of the Arctic sea ice. The same is also for the glaciers. The glaciers are, retreating in a huge amount of, we are just losing a huge amount of ice, and this is what is happening in the Antarctica and in Greenland. So these are, again, other indicators. So we are also losing a lot of ice, and of course, losing ice means losing ice from the ice sheet means sea level is rising, and of course, sea level is rising. So another indicator is telling us that the sea level is rising, and now is rising at a level of more or less 4 millimeters per year. Of course, this is just an average values, and it depends where you are around the planet. The sea level is rising for two main reasons, actually. One is because we are just adding melting ice in the oceans, but also because the oceans are expanding. So we can say roughly the sea level is rising 60% because we are adding more water in the oceans. 40% is because the oceans are expanding. And why the oceans are expanding? Because, they are accumulating a huge amount of heat. So all the extra, mostly the extra heat that we are just producing because of the CO2 that we have emitted in the last 150 years have been just stored in the ocean. So we can say that 93% of the extra heat have been already collected by the ocean. Only the 7% is in the atmosphere. So we have to say thank you to the ocean if the temperature now is only 1.5 degrees more than in the past. But of course, the ocean is doing this kind of job not for free, actually. So they are, expanding the volume. That means the sea level is rising. And this is just to give you an idea on how many centimeters we have already gained from the beginning of the previous centuries. So we already gained more than 21 centimeters. This means that in 19, so at the beginning of the last centuries, for example, the aqua alta in Venice was for sure less frequent than today, just because the mean level of the ocean and the Mediterranean Sea was lower than today. So, but what about the future? So where we are in terms of emission, where we are going actually. So here you see a number of what we call projection, scenario, that are the temperature that we can reach, the mean temperature that we can reach depending on the level of CO2 concentration in the atmosphere. So now we are here where you can see this red point. So it seems that we are not, following the worst, let's say, projection, but we are not, again, not very close to the best projection. So we are in a sort of a middle, let's say, territory. And we need to understand what can happen if we are a little bit above this threshold or a little bit below this threshold. And this is the, let's say, the game that the IPCC is doing every 5-6 years. So the game is just to project the temperature, the global temperature, for different level of emission. So the first, the upper left panel means what happens if we are systematically around 1.5 degrees. Here, below on the right is the worst scenarios. So between these two scenarios, we can have different impact, different, of course, also mitigation strategy, but also different adaptation strategies. This is also for the water. What happens to the hydrological cycle? Depending on the level of CO2 that we will reach in the next 10, 50, 100 years, we will have a different distribution of the water. Of course, the water will be always the same for every scenario, but the distribution will be profoundly different. And of course, also for the sea level rise, we will have different, let's say, projection. So we can gain something like more 20, 30 centimeters compared to the actual level for the best scenario, or we can gain other, let's say, 60 centimeters, or in case we will lose more, ice from the Antarctica, so this is a very dramatic scenario, we can gain more than 1 meters in terms of sea level rise. But this is, again, an average values. So the IPCC knows that this is an average values. So we cannot apply these values everywhere in the world. We need to assess the sea level rise in a very careful mode, depending where we are in our planet. And the IPCC is so clear that they just say in the IPCC report, in the last two IPCC report, that all the information coming from the ocean cannot be simply translated to some very small sea, like the Mediterranean Sea, that is like a lake, actually, for the entire, let's say, our planet. And why they say that be careful with this information? because what we provide for the Mediterranean cannot be reliable, 100% reliable, because, I mean, mostly of the global models used for the last two IPCC reports just represent the Mediterranean like this. You see, it's a very simple, rough representation of the Mediterranean. There is no connection between the Atlantic. For most of the models, the IPCC models, they don't have connection between the Atlantic and the Mediterranean Sea. So they see the Mediterranean like a lake, actually, not a sea. So that's why the IPCC, in a very correct way, say, okay, for the Mediterranean, be careful. What we say for the Mediterranean must be assessed in a very specific way. So this is what we are doing as a community, as a Mediterranean community. So we are trying to do our best to represent the Mediterranean in a climate system. First of all, we need to open the connection between the Atlantic and the Mediterranean Sea, because we know that the connection is very important. Here you see what happens in the Strait of Gibraltar. You know there are a lot of physical, let's say, mechanisms. There is entrainment, mixing, and the Strait of Gibraltar is working also as a hydraulic point. I mean, so you know that the sea level in the Atlantic is higher than in the Mediterranean Sea because of Gibraltar. Of course, all these stuff are not considered in global models. So starting many years ago, we started to work I mean, just to understand how Gibraltar works, if a model is able to represent Gibraltar. And we did a lot of effort to understand the physics of the straits and what are the limits for a model to represent the Strait of Gibraltar. So we did a lot of experiments. We did the first experiment in which the resolution was 200 meters. And we did, of course, a lot of comparison with the data. But at the end, we discovered that the 200 meters resolution is good, but the physics of the model can have an impact on the resolution. So we did an extra effort, I mean, changing the model. So starting from the Princeton Ocean model, we moved to the MIT GCM model. So from Princeton to the MIT, we just moved from one university to another university. I mean, increasing the resolution, increasing the physics, increasing the bathymetry representation. And at the end, we came to this representation that was the best at the time in terms of physical representation with a model of the dynamic of the Strait of Gibraltar. And you see the difference between the POM model and the MIT model. So on the left, you see the POM model, on the right, the MIT model. Of course, the MIT was also non-hydrostatic, so we were able to capture all the non-hydrostatic features like this bore generation and propagation. But here the problem is the MIT was at 25 meters resolution meters. That is very high resolution. We cannot use that resolution in a climate model. So we did a sort of analysis. What happens if we try to reduce the resolution? What is the minimum resolution that we need to retain all the physical, let's say, stuff inside the model? So we also try to understand if the non-hydrostatic feature was important in terms of climate simulation. And at the end, we came with these results. So 200-meter resolution is enough. And the non-hydrostatic feature is not so important. For example, if you look here, the hydraulics of the Strait of Gibraltar, if you do the simulation with without the non-hydrostatic feature on, I mean, the hydrostatic behavior is exactly the same. So at the end, we had the recipe. What are the minimum resolution? What are the minimum physics that we need to represent at the best the Strait of Gibraltar? We did the same also for the Marmara Sea. I mean, because at the end, if you have a Mediterranean model with the connection with the Atlantic, but without connection with the Black Sea, in any case, you are losing something in terms of hydrological budget. So we did the same exercise for the Black Sea, I mean, in particular for the Dardanelles and the Bosphorus Straits. And at the end, we succeeded also in representing at the best the exchange between the Black Sea and the Mediterranean Sea. And here you see how the model works in 3D, just to have an idea. Of course, there are papers, I mean, in which we do validation, in which we demonstrate that the effect of the winds on the Marmara Sea and so on. So I'm trying to give you just a flavor of what we are doing. If you are interested in the real results, there are the papers, and I can suggest you what you have to read. This is just to let you know that now, at the end, at some point, we had the receipt. So we knew what are the best representation for the Strait of Gibraltar, what was the best representation for the Bosphorus, for the Dardanelles. But again, there was something missing. Something missing in a climate models that cannot be, not considered in the Mediterranean, that are also tides. So in our climate models, we are also adding tides, because we cannot speak about sea level rise if we don't take into account also tides. You know, in Venice, we have sea level rise, we have aqua alta in Venezia, when we consider also tides. So that's why our model consider also tides. What you are looking here was the first 3D model that was able to represent at the best the tides in the Mediterranean Sea. And you see that the highest tide are in the Adriatic, very close to Venice, of course. So putting all this stuff in a climate model, we were able, first of all, to connect for the first time in a climate models the Atlantic Ocean with the Mediterranean through the Strait of Gibraltar, with the correct representation in terms of physics and processes like tides. Then we did, of course, an analysis of what happens in the past. So just looking the differences with our model and reanalysis. You know, the differences is a reanalysis is also assimilating data. In our case, is a climate model, we cannot assimilate data. So the fact that the model is very close to a reanalysis means that the model is very reliable in terms of climate projection. Here you see how the model performs in terms of circulation, but we use this model in a particular way just to assess the sea level rise in the Mediterranean Sea. So here you see how the model was able to represent the sea level in different parts of the domain, in the Atlantic box, in the Western Mediterranean, Levantine, and for the entire Mediterranean Sea, compared with the satellite data. And the model was able to reproduce very well, let's say, the sea level rise for the past. And then we did the climate simulation. So here you see how, for example, the temperature will increase for the RCP 8.5 scenario. And you see that slowly we are, trying to reach the 2100, so the next centuries. And just to, let me see if I can spoiler the end. By the way, we will reach more than 5 degrees more than the present in terms of temperature. In terms of sea level, sorry, here we have a problem with the orientation, but this is not important because what happens is something like that. This is what happens to the sea level rise. So year by year, you see that the sea level will increase. And there are also some features very interesting. You see that the Black Sea is showing more internal variability, and this is not a surprise because the Black Sea is small and depend a lot on the river discharge coming from the river Danube. So it's more, let's say, there's much more variability. But again, this is how the sea level is rising. But if we want to assess the information for a policymaker, or we want to go to a measure saying, okay, the sea level is rising, but this is only part of the story, because the cities and ourselves, we are not in the middle of the sea, we are just in front of a shore, actually. And also the shore can have, a movement. So we have to take into account also the land movement. This is what we have done. So taking also the new Copernicus data for the vertical land movement, we did this, let's say, preliminary analysis. So combining the sea level rise from one side and the vertical land movement on the other side, we just assess what can happen in the future for some places in Italy. This is Pianura Pontina, that is just south of Rome. And you see what can happen more or less around 2030, where you see the blue means that the water can flood this area. And of course, in 2050, we can flood more and more regions. And of course, by the end of centuries, more region will be flooded. The same for Rome. This is just the coastal zone of Rome. This is where the Tiber, river Tiber, the runoff of the Tiber River, and all these regions that are, I mean, very close to the Fiumicino Aeroporto actually will be flooded in the future. And we are also able to assess the amount of which kind of let's say land will be flooded. There's land that are used for, it's a urban land, or it's used for agriculture or whatever. And again, this kind of exercise, we can perform this kind of exercise now everywhere around the Mediterranean. But again, this was just for one scenario, that is the RCP 8.5. But now we are using our couple model to do also a more let's say a complete assessment. So using the couple model, this is our couple model, we explored not only the RCP 8.5 scenario, but also the new climate scenario, the CMIP 6 scenarios. So using the new scenarios, we were able to understand what happens if we are very close to the Paris Agreement in terms of CO2 emission, or we are very far from the Paris Agreement. And you see, this is the Mediterranean SST. In green, you see the best scenario, in red, the worst scenario. And you can see we will gain, degrees, a lot of degrees actually. That means we will destroy the deep convection in the Mediterranean Sea. We will reduce, we can reduce the deep convection with also the environmental, let's say, consequences. What happens to the sea level rise? Again, even in this configuration, the model was able to reproduce very well the sea level rise. And here you see how our simulation works compared to the MDT, that are just the satellite data. So in INCAS configuration or historical configuration, the model is doing a very good, let's say, job. And this is what happens to the temperature. This is the scenario, the 2.6, 4.5, 8.5 scenario. So what happens for the 4 seasons in terms of temperature? And it's very simple to explain what are going to happen if we don't do nothing in terms of mitigation. The same is also for the precipitation. And what is surprising, but is not so surprising actually, most of the reduction in terms of precipitation will last during the winter season. So during the winter season, there will be a very strong reduction of precipitation. What about the heat wave? You know, heat wave will increase, but heat wave will increase everywhere, also on the sea. And this is, for example, the increase of heat waves, for example, in the Adriatic Sea, for the 3 different scenarios. And as you can see here, we will have more than 3 months of heat wave stress for the Adriatic Sea by the end of the century if we don't do nothing in terms of mitigation. The same also for the sea level rise. Sea level will rise in different way depending on the scenarios, but what is important is that these data are more reliable than the global data, the global models, because, we can have also the high frequency information. So this is how the sea level can change in Genoa, Naples, Venice, and we have high resolution data in terms of frequencies, but also in a spatial way. And these are very important. This kind of data are fundamental when you want to do impact studies. So we don't need only the average values, but we need very specific values at high resolution in terms of space and time. Finally, this is my last slide. Actually, what we are doing is also now to move from this kind of models to a new kind of models where we use a very, very high resolution models. This is a model that are 2.5 kilometers resolution for the entire Mediterranean Sea for climate projection, because what we have seen is that high resolution is important when we want to assess the high frequency of the high, let's say, the weather event that are very disruptive. So this is the new generation of couple model that we are going to develop, and this will be done in a European project that is starting next month. And this is just a list. This is not a complete list, but this is a list of papers, more or less, that is a compendium of, I mean, what I've just described before, and that's all.
But you are perfect. Okay. So I think we can thank a lot Mr. Sanino for this very interesting review on what happened in the Mediterranean and what are the projections for the future. So probably if we have questions, we can discuss with you during the lunchtime or... But again, thank you very much for this lecture. And I think we can now welcome the next speaker, which is Catherine. And you will talk about regional needs for hydrography from research vessels in the Mediterranean Sea. And I guess you will present some result of a survey you conducted within your group. Yeah. So thank you, Catherine.
How can I... Yes. Where is my presentation?
I will say like 2 minutes. And okay, but no, yeah. PDF or PPA?
PowerPoint.
PowerPoint.
I prefer.
Okay, but I will just tell you if you need. Don't worry.
Okay. No, it's not there? Okay. Okay, thank you very much. So this is not a scientific presentation because I will just present you the outcomes of an interaction that I had with you at the last annual meeting in Tangier, and also with some specific person from the MonGOOS community, because in the framework of the EuroGo-Ship project, we needed to interact with regional networks doing ship-based hydrography. So if you remember last year, I presented the EuroGo-Ship project to you. It was mentioned also this morning. It is a consortium of 14 partners. It has 36 months duration, and here you can see all the partners involved. So overall, the EuroGo-Ship project seeks to support the European community, which conducts ship-based hydrographic observations at sea to provide higher quality and sustainable data flows to a broad range of end users more effectively from surface to bottom. And the aim is to strengthen European capabilities toward world-class oceanographic science. And here in the figure, you can see a picture of what is the present landscape of marine research infrastructures. And EuroGo-Ship is trying to fill a gap, because for research vessel-based observations, there was no really a research infrastructure as a reference. So the key goals for this project are listed here. They are the key goals, the long-term aim, and the current activities. I will briefly skip to the current activities because this is what this talk is about. We are engaging with different communities to identify which are the potential services that can be offered by a research infrastructure like EuroGo-Ship. And we have been conducting interviews with Mediterranean scientists to gather these insights and feedbacks. This is the structure of the project. Here we have all the work packages. We are specifically working in work package 4. And you see inside work package 4, there is consultation with regional networks. We have done this for the Mediterranean community. Other partners are doing this for Atlantic communities, and other partners are doing this for the Black Sea. So here, I just want to give feedback to you what have been collected by myself in interviewing people from the MonGOOS community. So the phase 1 was done last year when I interacted with you during the MonGOOS annual meeting. The phase 2 was doing a semi-structured interview to a number of people doing research vessel oceanographic observations. And we had some interviews with a written questionnaire and also a discussion on Zoom. And the topics were pan-European coordination, training, best practices, access to facilities, quality control, data management and access, capability, certified reference material, software for primary quality control, and a European marine equipment pool. So to briefly summarize what I have been doing, I have interviewed 9 people from these different countries with what we called champions. So these were people that in the MonGOOS community were particularly engaged with this kind of observations and also were particularly keen to provide input to design the research infrastructure in the best way. So now I will go through all these topics. I will try to be very fast. And for each topic, that was a section of the questionnaire of the interview, I have summarized what is the current situation and the difficulties encountered by the community, and what are the needs that the community expressed with reference to the topic. So starting with the topic of pan-European coordination, the current situation and the difficulties encountered by the community where there was a strong recognition of existing models like Eurofleet to facilitate ship time exchange between different nations and different institutions. I realized that there is an absence of a comprehensive coordination mechanism and common platforms. But this morning we heard in the AMRIT presentation that might be something that is under development under the AMRIT project. So this would be needed to access information like on planet or ongoing cruises to avoid inefficiencies or fragmented efforts or missed opportunities for collaboration. And the community also signalized that keeping up with new technologies is a significant challenge for the Mediterranean community in particular, and there are major concerns about data accessibility and the need for clear embargo periods after the data are collected. So summarizing the needs expressed by the people I have interviewed, there is, first of all, the thing that all of them said to me is the importance of sharing ship time. So we don't want a ship going out underutilized. We want to be able to join research cruises organized by other institutions or other countries, but there is not really a common platform to organize this or to make it more efficient. So there is a call for a centrally managed European research fleet to support a more efficient and cooperative oceanographic research. Another thing that should be organized at the pan-European coordination and where a future Eurogo ship research infrastructure could have a role is training and expertise exchange. I'm talking specifically for ship-going personnel, both scientists and technicians. but also about opportunities for students to gain practical experience and to have a system where you can share specialized equipment and personnel between different institutions. So there was a specific part on the questionnaire and in the interviews about training. Here the current situation, the community encountered and the difficulties that the community encountered was a significant gap in training opportunities, particularly for technicians that are required to handle costly and complex equipment. There is a general lack of awareness about existing, if there is any existing training opportunities in this field, a lack of practical hands-on training, and especially this is true for at-sea operations, and a lack of targeted training programs dedicated to specific measurements. There's also a great concern about the retirement of key personnel, which is responsible for instrument support, maintenance, and specialized analysis equipment. So summarizing the needs expressed by the community with reference to the training, let's say, topic, is to prioritize the training of technicians, especially for at-sea operations, to have some sort of onboard mentoring. So there is a preference for practical and hands-on training, so onboard like floating universities or courses that happen on board directly. Workshops, the organization of workshops and specific guidelines for data processing, data interpretation. Exchange programs for technicians, because many exchange programs are already in place for scientists, but not for technicians, or ship-going technicians, and also the recognition for technicians. So there should be a system that gives more recognition and credit to technicians for their critical roles in these ship operations. Regarding best practices concerning the collection of oceanographic measurements from ships, the community is aware of existing best practices, but there is a sort of uncertainty about their consistent application across different teams and different projects. There are existing best practice catalogs, but they are seen as to be too general and lacking in specificity about how to implement them. The existing sources of best practices are also quite scattered, so you can find them in scientific publications or in online repositories, and this makes it challenging for the community to find a comprehensive guidance on which best practice protocols to use. There's also sometimes a lack of official endorsement, so who is telling me that that is really the best practice that I should use? So here also EuroGoShip could have a role in making an endorsement of specific best practices protocols. And also there is a request to have a sort of real-life instructions, because sometimes best practices cannot be applied because of non-optimal conditions that can occur during research cruises. And many of the protocols that are followed are really relying only on verbal instructions. So the needs expressed by the community in this regard is to have more specific and detailed best practices. EuroGoShip should play a key role in advancing and standardizing best practices, and maybe try to make a sort of certification or a EuroGoShip label to ensure compliance with the endorsed best practice. A centralized platform for best practice protocols, including state-of-the-art protocols, is essential in this regard. So for quality control, I'm trying to run a bit more because there are some topic left. The difficulties encounters were that there are, in general, consistent challenges in applying the quality control procedure. There is a shortage of skilled personnel which are recognized and supported to do this task. And there is also a cost and a logistic issue to send equipment abroad to perform regular calibration. So the needs expressed here are to have the provision of standardized quality control tools, and maybe also this is something foreseen in the AMRIT project. Adaptability, the procedure should be adaptable to specific goals for each study, like climatic studies or short-term projects. There should be, again, a recognition and a support of people doing this kind of job of performing the quality check. And of course, the importance of adhering to the FAIR principles was also stressed. So then we asked the people, is it a service that the Eurogo ship research infrastructure should provide softwares for doing the primary quality control of observational data, and what is the situation? So many people are already using maybe homemade tools or provided by the manufacturers, but the complexities of some of these tools can also be a barrier, so there is a need of a more user-friendly softwares. And there is a challenge in integrating various types of data, so from CTD or from bottles, and these can be a very wide range of type of data. And there is a poor availability of documentation on the standardized tools. So the needs expressed here are we need a higher familiarity with quality control tools, and Eurogo ship could create, recommend, endorse, and put like a seal of approval to user-friendly tools to conduct this primary quality control. Let's see how many there are. I'm missing. Okay.
You have to conclude.
Yeah. I mean, I'm going through the topics, so maybe I will skip some of them. So the topic about capability was: is it a service that we can demand to Eurogo ship to have a general platform, a common platform where we can exchange skills between different people from different countries concerning the use and the data management of this kind of measurements? And here you can read the needs that were expressed. And finally, about the data management and access, there were reported to me challenges in the data management and access. There is not really, the current platforms do not adequately highlight the institutions and the individuals that are responsible for providing the data. And there are also reported users that face challenges with data discovery. So even myself, sometimes I cannot find my own data in the repository, even if I know I have submitted them there. So there is a need to make this more user-friendly, and the role of Eurogo ship could be to assist and streamlining the data submission process for data coming from research vessels. So I wanted just to report back to you, because you gave me a lot of input to do this deliverable at the end in the project. So I also wanted to thank you for the contribution, the discussions we had last year. And if you want to give me some more ideas or inputs on this regard, I will be around. Thank you.
Thank you, Catherine, but so much result to present in 15 minutes, so we have no time for question. I think it's very important for MonGOOS to have access to this kind of information. Is the report available, freely available?
Yeah, I have to deliver the report at the end of November, so that it will be on the website.
Okay, so feel free to share it with the MonGOOS community. Thank you. So the next speaker is our local host, Manolo Vargas, and you will speak about observation from fixed station and campaigns.
Well,
more or less.
I think that maybe, where is the mouse? You lost my mouse?
No,
yeah.
never.
No, ciérrala mejor y entonces...
Mira aquí. ¿Dónde estás tú?
Aquí abajo del todo.
Corta.
Okay, vale.
So Manolo, you have 15 minutes, but if we have time for question, could be great. So do your presentation in 10 minutes or 12?
15 minutes.
10 minutes, perfect.
In 12, you tell me. Okay, so first of all, I have to apologize because we are changing now the subject and a little bit more boring. We are talking about statistics. And the reason, the motivation for this presentation is that, okay, maybe some of you know that the Institute, the Spanish Institute of Oceanography, we have this survey that we repeat 3 monthly, 4 times a year, 1 time for each season of the year. And you could say, why you do that in that way? I could say, yes, we want the coverage of the whole Spanish Mediterranean, but maybe it's not exactly the truth. Some time ago, we have on a station, we repeat it monthly. So why you change this strategy from monthly sampling to 3 monthly sampling? My experience after many years is that each one makes what he can, simply. At that time, we had a small boat, 7 meters, so we could go to the sea every month. But it was very small, so we could not go far away from these stations. Now, we do not have, we also have this monthly station here. Now we do not have this small boat anymore, but we have a regional boat, so we can cover all the Spanish Mediterranean, but we cannot repeat with this high frequency. So the question is it useful for us? I've heard many times along my career the criticism from biologists, mainly that, for instance, for phytoplankton, chlorophyll, etc., this is not a good sampling, monthly, 3 monthly sampling, because you have all these filaments, mesoscale structures, so you have this high spatial and temporal variability. So the question that we asked ourselves is, well, our sampling is good or not depending on the objectives. So this is the first thing we have to do, define what we want to achieve. So we are involved now in, there is a European Union directive, the marine strategy. So what we have to provide is information about the state, the health state of the Mediterranean Sea, our national waters. We have to provide which are the mean values which characterize the state of the sea, the range of natural variability, so we can detect if there are changes or if we have long-term trends for climate change or whatever. So we decided to make a statistical analysis to answer really this question. Can we achieve these objectives with the 3 monthly sampling? Is it better or worse than having one single station but with a higher frequency sampling? So what we did is we need to test this idea and, let's say, ideal data set. An ideal data set would be the one which is able to solve all the temporal and spatial scales involved in the phenomenon we want to study. Usually, if we are talking about in situ sampling, we do not have an ideal data set. So we use a data set, downloaded a product from Copernicus. These are daily, in this area, in these rectangles, this polygon. We downloaded daily chlorophyll data. I think daily sampling could be more than anyone aspire if we're talking about going with a sea. And the spatial resolution is 0.1 kilometer. So this is our ideal data set. What we do the next is in the stations of RADMET project, this is the name of the project, we are going to obtain daily time series for these transects and the coastal and the open sea stations. So we are simulating that we have this ideal sampling with our oceanographic vessels. So we have all these daily time series in all the points. What we are going to do now is we are going to subsample, simulating that we have a monthly sampling or a fortnightly sampling or a 3 monthly sampling, etc. Then we will calculate these statistics that the European Union is requiring from us. And we will compare them with, let's say, the ideal results. So we see if really we are achieving the objectives that we want to achieve. So the different methodologies or sampling strategies that we have tested are the following one. Well, the first one is using the daily data. If we have the daily data, this is the reference, the true statistics, the true time series. The second one is we go to the sea and we pick 2 data per month. This would be ideal too. The following one is we go to the sea and we subsample with 1 data per month, but we are going to choose the 15th of each month because we want the conditions in the central part of the month. This following one is more realistic. Usually the weather can change, the vessel is not available always. So we sample monthly, but with a random date. Sorry. And the following one is, okay, ideal. We have this 3 monthly sampling as we have, but in the central point of winter, the central point of summer, etc. 15 February, 15 May, 15 August, 15 November. Once again, more realistic, the date is random, can move depending on the ship availability or the weather conditions. And the final, this is ideal because we are testing the performance of our project, we are going to subsample this daily time series at the days when we have performed these RadMed cruises, okay? So, and now we are going to see what we obtain with this subsampling. First of all, sometimes we forget that what we have is, when we go to the sea any day, for instance, what we have really is a distribution, and you are going to, if we go now to sample, we will obtain one data of chlorophyll from the distribution from October. Obviously, some values are more likely to occur than others. So from this, with the reference method, the first one, the daily sampling, we have more than 800 values to characterize each month of the year. So we would obtain this. This is the ideal, the true seasonal cycle, and we have also the accuracy of our estimations. So what happens if I go with a monthly sampling? For instance, in May, one day I go and I get a value that will be one of this distribution. This is the true distribution from 800 values. Now, if my sampling is monthly, I have a time series of 28 years. Finally, I'm going to obtain 28 values. From these 28 values, I'm going to obtain my mean value, which characterized the month of May, and also the range of variability, let's say the standard deviation, because this is the information required from European Union. Finally, we obtain this very nice with the monthly sampling. I think that the result we obtain is almost the same that the ideal seasonal cycle. What happens if we go with a 3 monthly sampling? Well, this is for the standard deviation. There are some differences, but more or less it's quite good. What happens if we go with a 3 monthly sampling? For instance, have a look at the month of May. It's the same. We have 28 months of May. We have 28 samples for February. We have 28 samples for August and for November. So, we are able to obtain only 4 average values for February, for May, for August, and for November. But these values are exactly the same that we would obtain with the monthly sampling. Where is the difference? That with the monthly sampling, we also obtain the average value for January, March, etc. But these values are exactly the same that we obtain with the monthly sampling. So we could say that's not so bad. The problem comes now. We have to provide information about the 12 months of the year. I have information only about 4 months of the year. So, well, this is the comparison with the monthly sampling. It's the same. So we have to interpolate. You see that now we have some differences, but I would say, as I participate in RadMed, I would say, oh, that's not so bad. I like this quite close. Well, so we can evaluate really the error. We can calculate as a percentage of the true value, and we average for the whole cycle. So now we can do this for all the different subsampling strategies, and so we can see if they are good or bad. On the left, on the column, you have all the stations that we have subsampled. Now you have all the methodologies. The 3 first methodologies are monthly or bi-weekly sampling, and the other 3 are 3 monthly. You see that more or less this is for the southern part of the Mediterranean, Spanish Mediterranean, and this is for the northern part. You see, for instance, for the northern part, the average error with the monthly sampling is around 5%. And for the 3 monthly sampling is around 10%. You would say, not so bad. The question is, should we move to a sampling at a single point with a higher frequency? In that case, for instance, if this is our station, our fixed station, we could say, if someone requires information about another point in the Alboran Sea, I can say, okay, I will give you this information because this is the one I have from the Alboran Sea. Which is the error? Now we can compare the true seasonal cycles from this point with the true seasonal cycles for other point. Here there is 18%, lower than 20%. So you would say it's better to sample in one single point with a higher frequency than in all the points with a 3-monthly sampling. This is the error. But if I go here, 44, 62, 79, so it is true that when I use a 3-monthly sampling to produce a seasonal cycle, I can make, in this case, an error around 20%, and in this area around 10%. It's not good, it's an error. But if I use my station to provide information about a nearby region, the error is larger. So our conclusion, we prefer to keep this 3-monthly sampling covering this large area. To finalize, if we make the same to calculate trends in the horizontal axis, you have all our stations, and then here you have the trends, the linear trends that we obtain. In black is the true. We see that all the methodologies are bad. Why? Because the linear trends are very low, and the noise, let's say the high frequency variability, is very high. So we did one thing. We simulated some series 50 years long. How if we do not have 50 years of data? Well, we reconstructed time series with the same seasonal cycle, the same trend, and with the same statistics as the noise. And what we see is that the 3-monthly results for the seasonal cycle are almost perfect. But for the 3-monthly sampling, we lower a little bit the error, but not too much. There is a limit, no matter how long you make your time series. Why? The problem is not the number of data you have to estimate the mean value and the standard deviation. The problem is the interpolation. If our seasonal cycle was a perfect sinusoid, we would reproduce exactly the seasonal cycle with 4 data. But if the shape is not a sinusoid, we need more harmonics that we cannot reproduce. So we have more interesting, finally, in the case of the trends, when we get a 50-year long time series, the result will be okay no matter the method we use. Get your own conclusion, because I don't have time for conclusions. Thank you.
Thank you, Manolo. I have a question for you, but I will keep it for lunch. So next speaker will be, I suppose, Elena Mauri. Elena.
Yes, I'm
Wow. I'm afraid, but so you will replace Elena. Sorry, where's the mouse? Yeah. Wait it. Did you update your presentation?
Yes.
Manolo,
Hello.
there is not a presentation from Elena. What's your name?
Riccardo. Yes.
So it is a presentation later? Yeah.
For who? The name? Claric?
Mauri.
Mauri.
I did not say. Go to the following one. I'm going to check the drive, okay?
Okay, so.
Is that okay for you?
Yes, no.
Okay.
You can come with me.
Ricardo.
No, it's inside.
So,
Vale, mira, y aquí tienes la de Claric, ¿vale?
¿vamos a hacerla ahorita?
Haz la siguiente, la que tú quieras, ¿vale?
Bueno,
Hay varias, cambia la que tú quieras
primo,
y voy
Pablo.
a descargarme ¿vale? Cualquiera de las que haya, ¿vale? No, esto es porque la de Claric está aquí, ¿vale?
Sí, pero no es de Clarica, ahora está
No,
de...
lo sé, pon la que quiera, digo que para que otra que falta ahí. Ponla a alguien que esté seguro, ¿vale? Vale, no, pero voy a descargarla, pasa cualquiera.
Sí, pero
¿Quién
lo
hay
siguiente
ahora?
es Lorente, que no está aquí también.
Bueno, entonces, ¿y Novelino?
Sí, pero mira, pues después
Ok, pues vamos al Google Drive.
va a Google Drive, imagino que es mejor.
Claro, la de descargar antes de las 12 de la noche, me va jodido.
Wait. I was on time, Manolo.
Ya.
Yeah, but we don't have it also in the local document. We are going to the drive, Vanessa, para ver si tenemos la presentación online. Porque aquí no está en el...
Okay, MonGOOS workshop, local presentations, so observations here.
Deja este abierto, ¿no? Lorente... Maori.
Mari,
Sí,
okay.
sí, perfecto.
So you download it. And now let's go to...
So this is the last presentation. This is the last
No,
presentation.
there is one more after.
One more after.
¿No puedes abrirla directamente de aquí?
Puedo, sí, sí.
Sí, porque nos vamos a hacerlo lo mismo para la siguiente, ¿no?
Vale, perfecto.
No, da aquí.
No?
Okay. Presentation.
Y
So I needed to be the fastest.
¿Vista del presentador? Here? No. Yes. Okay.
pero no aparece en la televisión. On the TV, ¿no?
No?
No aparece en la televisión.
Ma perché non facciamo
Creo que es
così?
mejor descargarla.
Sí, pero que vamos a perder tiempo para la siguiente
¿No?
también.
¿Seguro?
Sicuro?
Vale.
Bueno, perfecto. Gracias.
Okay?
Bueno.
So we are ready?
Yes,
I
you
can
do
start?
it. Thank you, Ricardo.
Okay. So,
Preguntas for question would be perfect.
okay. 5 minutes. I have only 5 minutes. Okay. Thank you. So now let's move to extremes and the observation of this extreme through a multi-platform approach, but in particular through the use of the Argo float profile. In the last 20 years, the deploy in the Mediterranean exceeded 19,000 profile for temperature and salinity, as well as 40,000 profile for biogeochemical algo. And all of these profiles recorded by these high quality data are really useful for climate change study, but also for extreme events. In the global ocean, the Argo float have proven useful for describing extreme event, and also these were applied for the Mediterranean region. And now I'll report to you 3 case reports regarding Medicane, marine heat waves, and density gravity current that can represent something like extremes. In particular, the medical Apollo was the main object of a study published in Scientific Report in 2022, in which we analyze the effect of the Medicane on the water column structure. This Medicane affected the Ionian Sea, causes huge damages and 7 fatalities. And fortunately, during the event, as you can see in this figure, autonomous instruments such glider, such Argo float and drifter sampled the area. The symbol represents the Argo float position during the event and the pre and post storm, while this arrow represents the trajectory of the Medicane that we reconstructed through statistical methods, and the black line represents the trajectory of the drifter that give us the possibility to investigate in detail the effect of the Medicane on the water column. The surface circulation in the Ionian Sea was particularly chaotic and characterized by the presence of cyclonic and anticyclonic structure. And in particular, the Medicane affected a cyclonic vortex close to the Sicily coast. Below the drifter, this is the time series of the drifter that recorded the sea level pressure and the current speed. And during the event, the current speed exceeded 1 meter per second, concurrent with a minimum in sea level pressure. So to better understand the effect on the water column, that is the main object of this work, we decided to divide geographically the area using the sea surface temperature anomaly and wind stress. But we don't have any information and any Argo profile inside in the center area of the Medicane, so we decided to use the model, so to apply a multi-platform approach to improve the description of the impact of the Medicane. But before doing this, we compare the Argo profile with the model product in terms of temperature and salinity, and the model described the characteristic are well respected. So we decided to investigate the effect of Medicane using the Copernicus model product, in particular the analysis and forecast. And what do we observe? We observe that the cyclonic vortex induces an increase in the cyclonic vorticity of the cyclone, and this produces an enhance in the upwelling that is completely different respect to the typical behavior of the ocean during the Medicane event, characterized by heat pump effect, so a transfer of heat in the deep layer. And this highlighted that the pre-existing ocean condition strongly influence and drive the response of the ocean to the passage of Medicane. Another important extreme that now are involved all the Mediterranean are marine heat waves, and in particular we analyze the vertical propagation of the heat during the marine heat wave of 2022, and this work was just published in the last Ocean State report. And to do that, we choose 5 different areas in Mediterranean Sea. In this map you can clearly see the distribution of Argo float during 2022 and all the Argo float surfacing. So the area were selected based on, obviously, the profile number, but using also the ocean heat content that this analysis was performed based on the work of Kubin et al. In 2023. So we choose the area characterized by the high ocean heat content anomaly. Then we use a particular method based on the comparison with the climatological values, and in particular we use the sea data net product, the climatology in temperature for considering 1984-2016. This method of the comparison with the climatology provide information about the different category of propagation. In that case, we define 3 different categories based on the vertical propagation, the shallow propagation down to 150 meters depth, and intermediate and deep over 700 meter depth. What we observe for the entire Mediterranean is that the vertical heat propagation extend from surface down to 1,500 meter depths in all layers of the Mediterranean Sea. And in the surface layer, the heat penetration are related to the stratification and advection from adjacent region. And another important result was that the region characterized by specific dynamics such as the deep water formation site or cyclonic or anticyclonic structure quickly distribute the heat in the water column. Then we can move to another extreme, that is the density gravity current. In particular, we analyze the formation and fate of the density current that were formed in the northern Adriatic. They are an important component of the central Mediterranean circulation, as produce a very dense water that go to the deep go to the deep Mediterranean affected the world circulation. And to that we take the advantage of existing observational network in the whole Adriatic Sea. In this picture, in this figure, you can see all observational network characterized by Argo, by fixed station, but I want to pay attention to the 3 moorings in the southern Adriatic that can be very useful to track this extreme event. In the picture on the right, you can see an Argo float time series spanning from the middle of June 2016 to the end of December that captured the passage of this dense water before spreading in the southern Adriatic, considering the potential density and the oxygen. And same, this is the time series recorded from the 3 deep mooring in the southern Adriatic. With the Argo float, we are able to track the spreading of this water both in the southern Adriatic and in the Ionian Sea. In this figure, you clearly see 2 TIAS diagram color-coded for the time that highlighted the presence of this point represent all the profile which the density exceeded the threshold for identifying the dense water, and this profile were geographically reported here, highlighting the spreading in the southern Adriatic at the time of the spreading, and also the spreading in the Ionian Sea. And here we are able to capture the deep water signal and the pathways of this water mass spreading in the eastern and the western part of the Ionian Sea. So thanks to the observatory built in the southern Adriatic to perform this type of research, because with this observatory we are able to investigate both long-term dynamics but also fine-scale phenomena as density gravity current. In conclusion, our analysis show how an Argo fleet integrated with in-situ data and operational model would improve our knowledge of a complex phenomenon related to the extreme event. In particular, the medical Apollo was the first time that we can observe an interaction within a cyclonic structure with this medicane, and the increasing vorticity changed the response of the ocean respect to what we observed in previous medicane. For the marine heat wave of 2022, the main result was that the warming were extending from the surface down to 1,500 meter depths in all layers of the Mediterranean Sea. And regarding the density current, the spreading of this water were observed in extraordinary detail for the first time, improving the knowledge of the dynamics in the central Mediterranean. Thank you.
Perfect timing, yes, but we were late, so maybe.
Yes, I know, so later. Maybe
we can let time for question during the lunch. I think so. Thank you very much. I think we can call our next speaker, who is Pablo Lorente. Let me, because there is a problem with the presentation. So you will talk also about marine heat waves, right?
Not extremes, but in the hardware.
Okay.
Just to let you know, I have a video, so in the Google Drive, I cannot play the video, I think.
No, but I have to...
Download the...
Tengo que descargarlo.
Sí, perfecto, perfecto.
¿Cómo se descarga? ¿Tú sabes?
No sé si dices ahí arriba.
Sí, así. No.
Ah, no, es la historia de descarga. Un archivo, seguramente. Si no...
Descargar. So Pablo, I think the floor is yours now.
Okay, thank you very much. Okay, good morning, everyone. This work is the result of a cooperation between the Metaphysical Department in Puerto del Estado. As you already know, climate change and extreme weather events attract public attention because of their impact on the marine environment and the human assets. While the global ocean is already experiencing a gradual warming, mid-level rise, we think that the impact of the climate change will be even worse and more significant over semi-enclosed basins like the Mediterranean Sea, and specifically in exposed sectors like the harbor systems. According to the work published by Izaguirre et al., which conducted impact analysis over more than 2,000 ports worldwide, those harbors located in the African Mediterranean Sea are expected to be in very high risk during this century, and Melilla Harbor is in fact one of them. So an unprecedented event, a huge storm hit the Alboran Sea and the Melilla Harbor with wave heights above 7 meters during the early April 2022. Beating all the previous historical records for each wave parameter. I can see the, okay. As you can see in the video, port operations were disrupted because of the severe weather conditions and the violent overtopping of breakwaters. One ship was evacuated from its berth and later sheltered to the lee of Cape Rastaksefi, and structural damages were reported in the seawall tip and also in several boats and marina pontoons. So the main goal of this work was to characterize the most extreme wave events affecting Melilla Harbor, and also to infer if they were compound events, that is, if a significant storm surge took place simultaneously, exacerbating the devastating effects. First, we compared the record-breaking event against previous extreme wave events to infer if they share or they were connected by similar atmospheric forcings at a synoptic scale. Secondly, we wanted to evaluate the response of the Melilla Harbor domain under the penetrating wave action in terms of high-frequency sea level processes. And finally, we wanted to analyze the long-term evolution of the most extreme wave events in the Alboran Sea. In this context, we used the ERA5 reanalysis, in particular hourly maps of sea level pressure and wind at 10 meters height, provided by the European Center. We also use in-situ observation from Melilla Coastal Buoy and Melilla Take Gauge, both sensors operated by Puerto del Estado. And finally, we use the Mediterranean wave reanalysis, which covers a 30-year period and is freely accessible through the Copernicus Marine Service. In particular, hourly wave data from Melilla Coastal Buoy were analyzed for the period comprised between 2011 and 2022. And the 99.9 percentile of significant wave height was was set to 4.45 meters, was used as threshold to identify the most extreme wave events affecting the Melilla Harbor. As you can see, 7 events were categorized and tagged chronologically, presenting values from 5 to 7.32 meters. Regarding the mean wave incoming direction, the predominant was the northeast direction, mainly due to the coastal orientation. So why did it occur? Which was the triggering atmospheric mechanism? As you can see, from a driving mechanism point of view, an inverted dipole of sea level pressure was observed with a high pressure system located in the northwest and very low pressure system located in the southwest. The resulting sea level pressure gradient, which was above 2 pascals per kilometer, gave rise to a very strong northerly winds, westerlies, that affected broad areas of the western Mediterranean and were channeled through the Strait of Gibraltar, following an anti-clockwise rotation around the low pressure core. And these very intense winds, above 20 meters per second, induce a very high significant wave height in the entire Alboran Sea. As you can see, this sea level pressure configuration corresponds to the so-called hybrid Rex blocking, which is a larger scale blocking pattern usually found during the transition phase from the omega blocking on the left side to the pure blocking on the right side, where the high pressure is located in the north and the low pressure in the south. And these particular large-scale blockings are atmospheric disturbance that are quite persistent, can last up to 10 days, and normally induce very intense weather events, as previously reported by Barrio Pedro et al. What about the previous 6 extreme events? Okay, but they share a pretty similar atmospheric configuration. All of them show what the so-called hybrid Rex blocking. It's also true the E5 event was close to become a pure Rex blocking during its clockwise rotation. And the main difference between the record-breaking E7 event and the 6 previous ones was the intensity, the magnitude of the sea level pressure gradient. In the case of the record-breaking event, it was above 2 pascals per kilometer, and in the rest of the extreme events, it was always below 1.3 pascals per kilometer. As you can see, there is a peak of wind speed affecting the entire Alboran Sea, with very strong easterlies flowing along both sides of the Strait of Gibraltar. And it's also true that the E6 event differed slightly, with moderate winds around, let's say, 15 meters per second, coming from the northeast and affecting the entire Western Mediterranean. And as you can see here in the significant wave maps, there is a peak over the entire Alboran Sea, and in all the cases, they share pretty similar directional incoming wave direction. The next question was, okay, when did occur these extreme events affecting the Melilla harbor? There is a preference for a specific stage of the year, so we decided to split the annual cycle into 7 intervals, 6 intervals evenly spaced of 50 days, and 1 longer summertime interval of 65 days that didn't impact on the metrics. As you can see, most of the early wave data above the 99th percentile were found in a specific period comprised between the 20th of February to the 10th of April. In other words, in the transition period between the late winter and the early spring. And this is precisely in agreement with all the blocking climatologies previously reported in the Western Mediterranean, because it's when the hybrid Rex block is found and induce this kind of extreme events. The next question we wanted to answer was, there was a storm surge. We analyzed the early data provided by our radar date gauge, and as you can see, the astronomical tide, represented by the red line, and the meteorological tide, represented by the green one, didn't impact on the evolution of the agitation inside the harbor. In particular, the meteorological tide just reached a peak of 13 centimeters, but then declined below 0. The main reason for that is that the low pressure system I showed before in a previous slide was located over the Gulf of Cadiz, in the other side of the Strait of Gibraltar. So we came to the conclusion that the overtoning was mainly due to the extreme waves. What about the rest of previous extreme events? Just the same. As you can see, the green line is always reaching negative values, so it didn't impact in the overtopping of the breakwaters. We also wanted to link, to establish the relationship between the wave conditions outside the port and the agitation inside the harbor. To this aim, we analyzed the 2 years raw sea level data provided by our Melilla date gauge for a 12-year period, and we got the agitation data, which have a period of below 30 seconds, by applying a 8-order Butterworth digital filter with a cutoff of frequency of 130. As you can see in the red time series, during the record-breaking event E7, the agitation reached a peak of 1.41 meters. not only exceeded the 99.9 percentile, but also the operative threshold defined for the Spanish harbors. In particular, for cargo ships, you can imagine right now, 1 meter is the maximum for longitudinal task and 0.8 meters for transversal operations. So in other words, the evacuation of the ship was a really wise decision at this stage. The orderly scatter plots evidenced the close relationship between the agitation inside the harbor and the significant wave height outside the harbor measured by the coastal buoy, as reflected by a high correlation coefficient of 0.87. The first scatter plot, the colors represent the mean incoming direction. So, as you can see, those high values of agitation above the 99 percentile, in the 89% of the times, they were related to waves coming from the sector comprised, the angular sector comprised between 50 and 70 degrees, taking clockwise from the true north. As you can see on the left and the right side, the agitation inside the harbor was also significantly modulated by the offshore period. In particular, the higher agitation values were found for peak periods above 6 seconds and mean periods above 4 seconds. So, broadly speaking, we can say that the S7 record-breaking event was motivated by a very strong swell with peak period above 10 seconds and significant wave height above 6 meters, coming from the specific angular sector that we said before. Finally, we also wanted to analyze the intra-annual variability of the 99 percentile of the significant wave height. To this aim, we used the Mediterranean wave reanalysis for a 30-year period comprised between 1993 and 2022. And we compute the trend maps for, on a monthly basis. And as you can see here, the red values represent upward trends and the blue color represent negative trends. And the tiny black dots represent those grid points which are statistically significant using a 90% confidence interval. In particular, we selected a specific black box to average the values and the trend time series for each specific month. You can see the first one corresponds to April and the second one to June and October, respectively. We can state that there were a significant trend, upward trend of 2 centimeters per year during the 30-year period analyzed, while the other two examples represent downward trends. So, summarizing, all those extreme events affecting the Melilla harbor share similar atmospheric drivers and usually take place in the same stage of the year, between late winter and early spring, and they induce a very high impact inside the harbor in terms of agitation, which compromise somehow the security and efficiency of the port's operations. Since the meteorological tide was negligible, we cannot categorize the analyzed events as compound events. It was mainly related to the wave records. And finally, we detected a positive trend of the 99 percentile of significant wave height for April. Regarding this approach, it's pretty simple, as you can see, and is portable to other harbors. Of course, it can be improved by using neural networks, for example, weather types or self-organizing maps. And the results here exposed could feed the future climate change observatory for the Spanish harbors that we further described by my colleague Marc Mestres in the afternoon session. And here you have the references, and just let you know that this paper just was published 2 days ago in the frame of the Ocean State Report 8, which is an annual initiative of the Copernicus Marine Service. Thank you so much.
Depende. If you want to eat, we can eat, and if you want to have question to Pablo, we can ask question to Pablo, of course. So if there are questions for Pablo, one question. No, we have no time, Vanessa, for you. Allez, just for you.
Okay, so thank you. Very, very interesting. I didn't know anything about this event. Did you have, very quickly, if not, we won't eat, plan already have a strategy of early warning system for these things like, also that you said that the evacuation of the ship was very wise. So if you have an early warning for 6 hours, 12 hours, you do something as driving, maybe will help. Do you have also a strategy in this? Very quickly.
Yeah, very quickly, I don't want to spoil Mark's presentation. It's part of the, we want to register all the extreme events affecting the harbors, not only from an infrastructure point of view, but also from the operations. The operations means money. So the Climate Change Observatory will be launched next year. It's reflected in the strategic mark published by Puerto del Estado. We want, first of all, to consolidate the Climate Change Observatory and register all the events and understand the triggering factors. And then the following step is just to implement early warning systems that directly goes to the harbor authorities to make that wise decision making.
Thank you.
You're welcome.
Yes, so I think it's time to eat, so thank you very much for all. I think we can thank again all the speakers maybe of this morning session. And Manolo have a very important announcement, so please be careful.
Very important announcement. You know, we are a little bit delayed, but the lunch will finish at the scheduled time, 2:30. Because, because this is more important. Then we have the coffee break at 4. It has to be at 4 because the people from the coffee say that at 4:30 they leave because that was their contract. So be here at 2:30 and then the coffee will be at 4, please.
I'm waiting for the green light from the chief. Vanessa. You have to say when we start. I think so. What time is it? We're late. Yes, we are late. Okay. Okay, so we will start again with observing system for monitoring climate change variability and detecting extreme event sessions. And we will start with a presentation from Diana from the Croatian Meteorological and Hydrological Services, and the floor is yours. Thank you very much. Please, if you can try to only speak for 10 or 12 minutes, it's allowed for questions, and it could be great. Thank you very much.
Thank you.
You have to do 10 minutes.
Okay. I could put alarm. Why not? Hello. My name is Diana Klaric. I'm coming from a Meteorological and Hydrological Service of Croatia. I'm one of the authors of this presentation of future monitoring of marine heat waves with the Croatian Met-Ocean database. We are a meteorological service, but we also have a long tradition of the marine service and marine meteorology service in Croatia. And it was the first time that we established serious measurements. And this is a possibility for us to present also not just meteorological features, but also some interaction between atmospheric and oceanographic features. This is just a fresh presentation of something was going on during this summer. So what I already said, we are state authority for marine meteor services for Croatia for more than 70 years. And in the definition of marine meteorology, that is connecting interaction between atmosphere and sea down to first 20-meter depth. It is important to understand that some definition are always necessary, and it's easier to speak with our colleagues. So Met-Ocean database, we established that Met-Ocean database. So the plan was 10 years ago, and it took us a long time to establish Met-Ocean database. But our idea was that we should establish interdisciplinary integration of meteorology, physical oceanography parameters, but also some biochemical measurements. But for us, as a service, the safety at the sea is top priority, and as we are working as for marine weather monitoring and forecasts and warnings for 24/7 for the all Adriatic. But for this purpose of this workshop, we also could say that one of the goals was also the Adriatic Sea climatology. So our goal was to put a system that should work at least 10 years to produce some climatologically valuable data. So, well, we started with 2022, but in period 2023-24, we just finished a very long period of test phase of 18 months. And during that period, we made the intercomparison between Met-Ocean buoys and automatic weather station, because we are measuring also atmosphere, and between Met-Ocean buoys and sea buoy at the shore. So Met Service of Croatia has a long history of network of the small buoys with the sea surface temperature, but these are shore buoys. So this new network consists of 5 Met-Ocean data buoys. 5 of them were, so at the north is Kvarner, Blitvenica, Viški Canal, Palagruža, and in the most south is Molunat. So this presentation will mostly look at the south of Adriatic, and this Molunat buoy represents south of Adriatic. One of the things is that we decided to put some also oceanographic measurements, but not lower than down to the 200 meters depth. So also Also, it's good to see that our bathymetry is Adriatic. It's very rarely we show the bathymetry, especially for the meteorologists. So we start to force them to understand the Adriatic Sea. It is for us, there are differences of the depth. So now this is our officially map of the Adriatic bathymetry, just to force people to understand that Adriatic Sea. If you have in one map mountains, why you don't have bathymetry? It is for me always a question. I haven't seen any map. Okay, it's the digression. So also all that it was by that METMONIC project. So this was a big project for Met Service of Croatia, modernization of all networks. So not just the buoys, but new weather radars were bought, also bought a lot of automatic weather station, up to 400 automatic weather station. Here is in this title, you can see that also there is possibility that this networks is also joining with our colleagues who are now here, for the two boys of Institute Ruđer Bošković, which are at the west of Istria Peninsula. So coming for the setup, well, we have meteorological sensors. Of course, for the safety of the sea, it's very important to have a dual meteorological system. And for the security of the sea traffic, it's very important to have the sea visibility over the sea. So this type of measurements are important for our duties as marine forecast and weather alarms. And, but for the oceanographic parameters, we bought system, very extensive measurements of the surface at buoy mast housing. It is so sea surface temperature, conductivity, dissolved oxygen, turbidity, and chlorophyll type R. But also we have directional wave sensor on the top of the buoy. And for the profiling, we also have compact CTTO down to the depth of 150 meters. So we put up to the 5 sensors in that depth. So actually, for the sea surface temperature, we have that on the buoy, and also 5 sensors in the sea. And with that also we bought current meter, and this current meter is just housing on the buoy mast, so it's looking downward. Okay. So monitoring marine heat waves. Once again, I would like that we also mention, yesterday somebody mentioned definition, so actually yes, anomaly of maximum sea surface temperatures are defined by intensity and duration. But some authors are speaking about intensity greater than 90 percentiles, some authors are speaking about the 99 percentile. American authors would like to mention that 99 percentiles is very safe. Yeah, then you are not obliged to count dates, you know. Nobody likes to count dates to proclaim some status, you know. So it is actually like that. But also Copernicus climate has this definition of, I'm sorry, I put some definition because everybody is speaking, but not everybody knows what we are talking about. So for the interaction between air and the sea, they said that for the marine heat waves, you should have extreme warm air masses in the blocking situation, increased solar radiation, weak wind-driven sea evapotranspiration, reduce mixing on surface waters with cooler deep waters. So our motive was this July 2024, when extreme maximum sea surface temperatures were measured during East Adriatic coast. So we will make intercomparison between two networks of the measuring sea surface temperature, and also some measuring in the deep. So also monitoring marine temperature examples, we also should understand what we are monitoring, who is measuring what, who is producing quality of the data, what you would like to achieve with that. And also if you try to produce some near real-time monitoring, we should monitor everything. So not just marine heat waves, but marine cold spells as well. So the case July 2024, South Adriatic, so the shore buoy of Dubrovnik measure 29.7 temperature, and everybody were excited, but our buoy, it was more, it measured 30.4 degrees, and look at in this small map Dubrovnik and Molunat. So our Molunat buoy is moored at the depth of 154 meters. So comparing just meteorological situation from the left, you could see the average daily temperatures from the left, all the time we are looking average daily temperatures in our service, and it is a web page, this graph. This is why I'm not translate that. And also the blocking situation, if you look, it was synoptical charge, little blue there is South Adriatic, but everything was blocked. All the rain was in Brussels, as I could say, from yesterday evening. Okay, so even WMO announced that in July we reached the absolute maximum of all measurements on air temperature at the globe. So it was, last year was recorder, it was in this orange, but this red is this year, so at the 22nd of July they reached that maximum. So what we see from our buoys, if you look at operator, we are looking a lot of meteorological and surface parameters for the oceanographic surface parameters. So on the top you can see from left side wind, and from the right side significant and maximum wave height. From the left side down you will see air temperature, this is red, and blue the right side is sea surface temperature, this is our first level 1.2 meter, and also from the left side you could see total radiation, so there were no clouds, nothing else, and also something else. So when you look at our data for the profiling, from the left side you could see temperature, salinity, and oxygen. And from the right side you could see just first two layers, because we notice early variability of sea surface temperature down to 10 meters, but not lower. On at the bottom right you could see our CTD acoustic current meter, and it was less than 200 millimeters of speed, so it is 0.2 meter per second. So we compared Dubrovnik with station with our buoy, and we were always hotter. But what is the problem? That when one outburst of the rain produce a lot of cooling of the sea surface temperature in the Dubrovnik, and this is due to this crust area. So crust area hiddenly contribute to the sea surface temperatures. So just it was moderate rain, but this catchment, underground catchment, is not visible. Just give me some time. And so if you look at where this coming from our salinity measurement of the buoy, you could see very easily how this salinity drops, so the fresh water came, and this was not visible for us as old-fashioned meteorologists, because we never looked at the salinity before. So just we compare all the graphs, we compare correlation between the oxygen and temperature, and also we look at what could we gain from the data from the satellite Copernicus daily products and ERA5. And we noticed that they are not sensitive enough. So look at this left graph, this is satellite daily products, so daily mean of temperature. This orange is ours, so we compare 3 points for the satellite data, all unsensitive to some cooling that appeared. And also we compare it with the ERA. So both of systems are not properly responding. We expect at least every 2 days that they will shift to our regime. No, it not. All the data took curve somehow. So this is operational data, you could download it. So maybe we downloaded something strange, but we think that it is not. We also look at, because of it, April, and same thing happened in the April. and so data are not comparable. And when you like to monitor this marine heat wave in general, you could use these values for Copernicus Mediterranean from the left side and the Copernicus Global, and you could see that for Copernicus Mediterranean there is that daily variability of daily data, but something happened in the end of the July, and this daily data started to look like averages. So this is some total error, but unfortunately also appears somehow, but not so strong at the global. Also, it's very strange that this data shows that we are almost always, so first graph is average blue, second one is 90% and 99%. Percentiles. So it seems that we are all the time in this. So just my conclusions: meta-oceans are excellent source of information about the sea air conditions during the marine temperature anomalies. Adriatic sea temperatures have strong hydrological impact, and salinity data are important. So meteorologists never thought about it. And future real-time data temperature monitoring should have both systems. So should monitor also this marine cold spell. And I think that at the North Adriatic, we will get a lot of it due to Bura, due to Po River, and things. So I think the system should have the both. Thank you. Sorry.
Thank you, Diana, for this presentation. No, Vanessa, we have no time for questions. Allez, because it's you. One, just for you.
More than a question is a suggestion and saying that I found the very, very interesting what the measurements you are taking, and I think should be included in our dashboard. If they are not included.
It must be.
It must be. No, it should.
Yeah,
okay,
yeah. No,
so they must be
really advocate for
included,
that.
and then because they can be very valuable information.
Yeah.
I was just this, once you fix all the problems that we normally have with buoys, I know this, and
It's new branch of activities. We were surprised with a lot of things in the data, and also with the task in front of us for the maintenance, especially this CTDs at 150 meters. Sometimes there are signals, sometimes not.
so for the coastal and also research is very important. So I'm looking for you to put the dashboard so we can share the data with the community. Okay.
Yes, thank you, Vanessa, for reminding that. Okay, no, next speaker is Marc from Barcelona, and you will talk about sport, climate change, and something else, probably.
The climate change observatory.
Resilience.
Yes, well,
It's a
climate
keyword.
change.
The floor is yours.
Thank you. I'll do my best. Right. Hi, good afternoon. As well-informed people, you'll probably remember this. 3.5 years ago, the global supply chain collapsed. For about a week, there were delays, shortages of goods, price increases, and massive economic losses, estimated at about $10 billion per day, American billions, but still a lot of money. In that case, it was because of the blocking of the Suez Channel, and it was an extreme case, but similar scenarios might become more frequent in the future due not to channel blocking, but rather to increase in downtime of ports due to climate change. Downtime is the time that the port, the harbor, cannot operate or is closed, cannot be accessible, and that leads to economic losses. Seaports account for over 80% of international trade. They are very relevant at all scales, from local to national. But they're also at the forefront of climate change vulnerability. And this point has been highlighted by many institutions at all levels, pointing out the fact that international trade could collapse again if we don't start implementing adaptation strategies to seaports. In Spain, this challenge is addressed by, within the national plan, National Climate Change Adaptation Plan, and also in the strategic framework, on the strategic framework for the port system of general interest. That is the set of ports that are of most relevant to Spain's economy. Within this strategic framework, there's a list of different strategic lines, and one of them that's called I can't get the thing here. And one of them that's called Eco-Proactive Ports has again a series of management goals, and one of them is focused on climate change adaptation. And to attain this goal regarding climate change adaptation of ports, they propose basically two aspects, two issues. The first one is to develop and implement adaptation plans for all the Spanish ports belonging to the system. And the second one is to develop what they call the Port Observatory on Climate Change, right, in OPCC in its Spanish acronym. What I'm going to talk about here is about the conceptual design of this observatory. So it's not a scientific talk. You don't expect fancy figures or important numbers because it's all quite conceptual. Right. According to the framework, the main objective of this observatory, of this OPCC, is to measure and characterize the effects that mid-ocean phenomena have on infrastructures, but also on port activities and on port operations, and to assess the vulnerability of these assets in the face of extreme events linked to climate change. And to do this, it proposes using a typical risk analysis procedure in which we try to determine the functional and ultimate limit states regarding operations and structures, but also risks related to environment, to social and to economic aspects. If we look at the framework's roadmap, it tells us that this observatory must be implemented next year, and it also expects that all the ports are fully adapted to climate change effects by the year 2030. So this observatory was initially viewed as a register of past events, extreme events that have affected Spanish ports in the past. And not only the events, but also the impact, how it affected the port, and also the costs associated. Right? Because as I think Pablo mentioned before, when we're talking about ports, the economic aspect is very, very important. But we've tried to redesign this observatory. What we know that happened in the past is very nice, but we also want to know what's going to happen in the future. So we've added this future component to the observatory, including climate projections and the assessment of future climatic risks, in the hope that with all this information, we can develop or derive a series of indicators that can be useful either for business plans or also to steer, evaluate adaptation plans. And this new design of the observatory also implies new challenges. For example, we have to develop new techniques and new knowledge regarding climate change projections, how to apply them at harbour scale. And we also have to address how we develop systems or tools that can process all this wealth of data and make it useful for harbour managers. So what we've, the core of this observatory is based on experience that was acquired during a project that was, that's called Eclipse, and we saw that for this observatory to be useful, it must be based on 4 principles. First one, flexibility, to ensure that the observatory can be adapted to any harbour whatsoever, to its characteristics, to its needs, and to its capacities. This flexibility also allows us to implement, or will allow, to implement this observatory in a step-by-step basis. So we don't have to have the observatory in full mode for each harbour, but it can be done as a progressive implementation. The second principle is integration. It has to be integrated in the sense that it must include past and future data, like I've also already mentioned. It has to include observations and numerical simulations, and it must include all types of potential events and potential damages that might affect the harbour. It also must be updatable, because we can derive risk values based on today's projections, but these projections will change over time. So we need an observatory that can adapt and can evolve, can be continuously revised to include new data, new observations, new projections, etc. And finally, and very important, is it must be consensual. And this consensus means that it must involve all the actors related to ports, from the port authorities down to the smallest of the commercial concessions, services, other users, in order to define the extent of these risk analyses, to evaluate the risks and possible adaptation measures, and also to implement and review these adaptation measures. So based on this same experience that I mentioned before within the Eclipse project, and based on the guidelines provided by the BIANC, we developed a methodology based on 4 steps. The first one is to identify, it is necessary to identify which infrastructure or services can be affected by climate change. It's necessary to perform a criticality analysis to see which of these assets are critical or not, which must be adapted immediately and which can wait. The second step is to assess the critical, what we call the key variables, the critical variables that impact operations or infrastructures in harbours, but also the response variables, how the harbour infrastructures or the harbour services respond to these forcings, by flooding, by interrupting loading and unloading of ships, affecting the working conditions. And as you can see in this list here, the number of key variables can be as long as you want. Once we've got this information, the third step is to perform risk analysis. This is a traditional method in which we combine the hazard, the probability of a given event affecting our harbour in the future based on climate projections, with the vulnerability, which consequences is that event going to have, measured in whichever way you want, and the exposure, which is a measure of the extent of that impact. And this should allow us to derive for each critical asset and each critical variable, forcing variable, a series of risk matrices similar to this one, which will eventually allow us to prioritize things. It will allow us to work towards adaptability. With this set of risk matrices, we can start redefining thresholds. The ones we have might be outdated. We can introduce tipping points. We can define which areas are going to be more vulnerable from a climatic point of view, what we call climate vulnerability areas. We can define safe operating spaces in which operations can carry on as usual, and we can also create a structured catalogue of adaptation measures that will allow us to prioritize which areas have to be adapted first and which are the optimal adaptation measures that we can implement there, right? From different standpoints, economic, technical, whatever. And of course, this observatory cannot do all this without an IT tool that should allow us to introduce, well, data on past events and future events, introducing the storm data that Pablo showed us before, and performing all a set of preliminary analysis, detecting trends, extremes, assisting the users in developing the risk analysis protocols, etc., and finally making all this information useful for managers or stakeholders in the form maybe of adaptation pathways, vulnerability maps, maintenance pathways, etc. Well, I might skip this because I'm a bit short of time. This is basically to illustrate that the amount of data we need to feed this observatory is not simply port layout and meteorogenic data, but we also need social data and economic data. And sometimes this is very difficult to obtain because part of this data might be secret, right? Secret, confidential, let's say. Maybe a port operator doesn't want doesn't want competitors to know how a given event impacted their business. To summarize a bit, this Port Climate Change Observatory is a stepping stone in what Puertos del Estado will call climate services, which will provide new data, climate warnings, and also new tools to insert all this wealth of information and to visualize all this data to aid in management and adaptation of ports. But this is the last step, and it doesn't come, we don't start from scratch, or it won't start from scratch. It will benefit from all the wide array of tools and numerical models that Puertos del Estado has already in operation, from the coastal and harbour monitoring systems to the short-term forecasting operational system developed within Samoa. So there's a large part of this data that's already available. And finally, if I can conclude, just a few remarks, just to mention that the shaping of this Spanish Port Observatory for Climate Change is taking place. Components have been defined, the conceptual model has been developed, and with the basic IT tools have also been, or a skeleton of these basic IT tools has already been proposed. It could be viewed as an evolution or an extension of the current operational systems provided by Puertos del Estado, which is the manager of these Spanish ports. And it is expected that this observatory will serve to support, well, scientific and technically based decision making, the monitoring, the follow-up and review of harbour adaptation plans, changing them if necessary. It will also allow to include climate risk indices within harbour adaptation planning. And eventually it will foster and promote the interaction, the involvement and cooperation between all the harbour actors and obviously the technical and scientific communities to try to derive a standard and homogeneous way to approach climate change risks in harbour environments. I think that's all. Thank you very much. Questions? I've been too fast.
Too fast?
I don't know.
No, but I have the authorization from the chief that we can have time for questions. because we are here for discussion also. So if you have a question
Okay,
to Mark,
so any questions?
feel free to ask. Oh. Ah, Matthias.
How do we define risk?
Can I speak here?
Oh, sorry. Well, it's complicated to define risk, but because apparently every field and probably every discipline has its own definition of risk. Here we try to define risk as a measure of the effects that, in this case, a harbour is going to experience due to the presence or occurrence of an extreme meteorological event. Sorry? It can be physical, it can be whatever. Generally, we will end up measuring it in economic units, but it can be, for example, limit the access to the harbour. That implies a cost to the harbour. Destroying a breakwater, for example. It could also affect other services, activities. Some operators that can't work properly because the water temperature is too high. So harbours are a very complex environment. So it's not easy to have a simple definition for this, but it can be any type of effect. Yep.
Other question? Yes, let's go.
I find it super curious that harbours are not yet prepared for the short-term future, like 100 years, right? One would expect you build in a little bit of a security margin and you're good for the next 100 years. What percentage do you think we underbuilt the harbours? Are we missing a meter height of the?
I think that depends. That depends on the harbour. I mean, most harbours.
But how comes? Can it be that bad in constructing harbours?
Yeah, but you're thinking of impact only in terms of probably sea level rise or waves like the case we saw. You're thinking of impact in terms probably of sea level rise and waves, but in harbours there's many more variables that can be important. Not only that, we can have rain, for example, water temperature, water acidity. One example that appeared during the Eclipse project that I thought was very interesting, and I always mention it, is how dry periods and heat waves affected the harbours. Because in some of the harbours studied within this project, this is funny, during dry spells and heat waves, it was more likely for the harbours to stop operating. Why? Because it was more likely to have wildfires. And for some reason, the hydroplanes that were used to put these fires out loaded the water right in front of the harbour. So when there was a wildfire, the harbour could not operate. So it's not just sea level, waves and things like that. There's a lot more variables that have to be taken into account.
Okay, thank you, Mark. We have to switch, sorry for that.
No,
You can continue the discussion later if you want. Next speaker is coming from Alcimar, which is the European glider manufacturer. So whatever, if the presentation will be good or bad, we don't mind. I think it's a very good opportunity for MonGOOS community to see how the private sector can indeed contribute to the observing effort in the Mediterranean Sea. So, Laurent, the floor is yours.
Thank you very much. As Laurent said, Alcimar is mainly known because it's a glider manufacturer company, but we produce as well data as a service. We contribute to European programs. And today I will show you the work we did within Iliad, which is where we've put a sensor called the UVP6, which is a zooplankton sensor. Iliad is a European project. It aims to create digital twins of the oceans with an S. Oh, sorry. Laurence? No. Maybe if I do this, is that better?
Sorry.
Muchas gracias. So ILIAD is a European project aiming at creating a digital twin of the ocean. One of them is in Greece, close to Kavala. And the aim of this DTO is to prepare for eventual oil spill. And it's using a large set of sensors. There is 4 ADCPs, 1 surface water quality system, 2 wave rider, which gives the swell, and we do as well glider survey in the area. So there is one part of the job which is to produce oil spill models in order to prepare authorities in case of these very nasty events. But we need to know as well the impact. And in order to know the impact, we need to have access to data in the region. There is a mobile app that has been developed for authorities to prepare reaction in case of events. And as you can see, the Thracian Sea is a sea that is pretty much undersampled. This is a 30-day of data where you have one Argo float and one campaign doing CTD work or XBT work. And if you look at 1 year period, you still can see Argo floats and campaigns, and the green dots are the glider data. So why did we decide to go in this region? First of all, it's because we cannot go where we want. We had to stay in Greek water, so we could not go in Turkish water, for example. But the most important part is to study the two basins that you can see here. You have Athos Basin and Thracian Basin. They are very close to each other, only a few kilometers apart. And the area is very complicated because of the Dardanelles Strait and because of the numerous river inflows that there is on the coast. It's not our first time there. We had a program called Odyssea, which is now finished, where we already did some deployments. And one of the conclusions of the studies is that we had a deep chlorophyll maximum, which is very symmetrical and very deep. And in theory, this means that it's dominated by picoplankton. So because we had another program, we decided to go and have a look with the UVP6. And the data has been published, and you can see the publication at the top right corner. So the UVP6 is a sensor that takes picture of the ocean. In fact, it's like a microscope in the water, and then you can find the zooplankton, the small particles that live there. And we did 2 deployments. We did 1 deployment in summer and 1 in winter to be able to see the difference between it. And we have an ADCP as well on the glider. Because we want to combine, in fact, data from the UVP6, which are pictures, with the backscatter index from the ADCP, and the turbidity, was the backscatter sensor from the FLBBCD, to make sure all those data match. And this is what you can see when you look at the 2 physical properties of the water, so temperature on this scale. And what is very interesting is the 2 legs you see at the bottom of the profile diagrams, because those 2 legs are the 2 legs of the 2 basins. So the 2 basins are very close one from each other, but the 2 water masses are very different at depth. Another interesting feature is especially in summer, where you can see that the salinity is very affected by the cement. So you can see that you have mixing, and you have different water masses that comes one to the other. And when you look at oxygen, same thing occurs at the very bottom of the basins. You have a very different signature in terms of dissolved oxygens. And for the chlorophyll, you can start to see that we have about the same amount of chlorophyll during winter and summer period, but it's very affected by wind forcing that we had in terms of layers. And I have to say that in my presentation, most of it is, I will present the data sets more than the results, but for the first glance, this is what you can see from these data sets. Here, what you have is a data that is given in real time by the UVP6. It's a data of the particle size and abundance, and you can see that the ocean, the highest point of the bathymetry give an increase in particle abundance. And you can see as well at the end of the winter season, a lot of particles close to the shore, and this is due to the very strong rain that affect us this year and the river inflows. Here you have the backscatter data from the optical sensor, where you can see strong coherence between the UVP6 data and the backscatter data, which is a very good sign of good data quality. And same thing, where the bathymetry is very high, you can see you have a lot of particles, and as well at the end of the winter season. But the good fun of it is a UVP6 sensor, which is producing picture, and those pictures, you have them only at the end of the mission. So when the mission is finished, you can download your picture. And thanks God, there is as well a software suite that comes with it, which is called Ecotaxa, because I know nothing about zooplankton. And this Ecotaxa suite will take all the images and provide little vignettes, small images about interesting features that we have seen. So we don't have to do the work, because the software has been trained with more than 380 million images. And with the glider, the good thing is that we produce a lot of images, because the glider stays 20 days at sea in this particular mission. And that is more than 100,000 images, only for our project. And this is the cool ones, which I will not describe because I am not able to, but probably somebody will do. But what you can see is that you have a lot of copepod, which is one of the target one of the species we will target. 80% of the picture are called detritus. It's something, it's like snow or particles in the water which are not identified as being zooplankton. So the first things we did with this data set is to have a quick look at it, and you can see that in winter and summer deployment for the three major species, which are Appendicularia, Rhizaria, and Copepoda, you can see that the distribution is about the same, but of course the volume is very different. Now you can see the picture of the first species, which was Appendicularia, and you can see that most of them are close to shore, but they are as well present in abundance on the top of the cements in between the two basins. Same thing occurs with the Rhizaria, where they can be found almost everywhere, and especially in deeper water and close to shore. But once again, and particularly during summer, you can see a higher concentration where the bathymetry is high. And finally, copepods, they are found mainly close to shore. And there is an interesting factor with the river inflow during our winter experiment, because there has been like a mini bloom in the water with a lot of copepod. But once again, you can see that bathymetry plays a major role in the presence of those species. So I wasn't the one supposed to present today. It was Félix Margerier, who unfortunately was not able to make it today. But most of this work has been inspired by a paper from Thelma Panawi-Otis, where they did the same kind of studies with 5 months of data close to Nice. And this has been published. At the very moment, we have a glider in the Black Sea. This we want to monitor mainly oxygen, and we have a SUNA sensor on this glider because we want to be able to monitor H2S with the SUNA sensor. And next year, because it was said this morning that it's important to know in advance what people will do, next year we will have our long deployment from Morocco with Hussein Nibani in order to capture data from the gyre in Aldebaran Sea. Thank you very much.
Thank you very much, Laurent, for doing this presentation. I know it is not an easy exercise to do a presentation instead of someone else, but I think it was super interesting and always exciting to see glider data. You presented the data set. I guess there are probably many scientific questions. Great.
Great.
Lady first, please.
How do you recognize images of the black hole? How do you recognize them? Each from other?
Well, this is the work of the software Ecotaxa. It has been trained by artificial intelligence to recognize all the species. So this is done by a laboratory in France called IMEV in Villefranche-sur-Mer. They have many years of experience, and we rely on that.
The recognition. Yeah.
Exactly. And if you want, they can. We didn't do that yet, but they can check your image with a human in order to create a data set to train in your. Well, they have specialists that would train a data set for your own region.
I think we have time just for many questions. See, let's go.
Thank you for the excellent presentation, and also I was very happy that I saw some work in Greece. The first question is, what is the energy consumption of the UV6 per day? That is more on the technical aspect.
So in terms of watt hour, I don't have it from the top of my mind, but I know there has been a mission made by Carlos Barrera, which is more than 28 days. And this mission is about 20 days with all the sensor, 22 days with all the sensor I've given. But we start at 30-meter isobat, so we use a lot of energy to go in deep water.
Thank you.
But it's okay. It's not a horrible sensor.
And the second part of, you just mentioned that you deploy a glider in the Black Sea. Okay, I was deploying last year or 2 years ago, I think. Did you use it is on the shelf? I didn't get it. So you are on the shelf to the Danube cone, or it's a shallow glider?
So, well, I don't have bathymetry on this presentation. Oh, you don't see my screen. So we start on the shelf. We start off the shelf from Romania. Is Razvan Metreu that is in charge of that. And we go up to the shelf break to do 500 meters zero, and we come back. And this is about the trajectory. And well, we had some problem because it's a war region, so at some times the glider end up being in
So you are primarily
Crimea.
on the shelf?
Yeah, mainly shelf. Yeah.
Okay.
maybe one last questions, and after we switch.
Thank you.
Quick.
Quick, yeah. I have a question. In the measure that makes the sensor, is quantitative or only qualitative? It's a screenshot of the plankton community, where you can estimate the density of this community.
So this is part of the work. Of course, we are not everywhere, so it's a quantitative measurement because we have pictures and we count them one by one. It's a qualitative measurement in the sense you are just at one spot, and it doesn't mean that the surrounding area is the same. And you have seen in this very short mission that the variability is very high from a region to another. But what we wanted to compare is as well the results from the other sensors, the ADCP and the turbidity sensor, in order to see what kind of proxy we can find between the two.
Okay, thank you, Laurent, again. Thank you. Thank you for the questions. Next speaker will be Maximo, I think. Yeah? Maximo Garcia Jove de SOCIB, and you will talk about high resolution observation and modeling.
Thank you. Thank you very much.
The floor is yours.
Thank you. I think it's working. It's working.
Perfecto. ¿Es la tuya?
Sí.
Attends. Se supone que funciona.
Thank you. Thank you for the invitation in the MonGOOS session. I will speak about the subduction area in the Western Mediterranean Sea. The subduction area are important to vertical velocity, to subduction heat and tracer to the deep layer. This work was done in collaboration with SOCIB modeling facility, glider SOCIB facility, and the MC team from the Massachusetts Technological Institute and the script glider team. Principle, I want to present SOCIB. SOCIB has open multi-platform data access. We created a new web page we released on September. We have several multi-platform. In the schedule we can see glider, drifter, Argo, float, and the catamaran. And particularly I will present the work in the facility, modeling facility where I work. So, I want to present Calypso as an application in the multi-platform observational. Calypso is titled Korean Lagrangian pathway from the surface to the interior. In this schedule we see the typical sea experiment with a ship crossing with CTD frontal area, we deploy glider, Argo at the same time to monitor the subduction area in a cross-front. The goal of Calypso is understanding the vertical movement of the water from the surface to the deep water. In the sketch, this is an anticyclonic movement. We see a vertical displacement to the deep layer, and this is a satellite image that structure we try to capture. So in the background, the vertical velocity is a strong function of the scale. In the spatial wavelength spectrum from the surface, we have the meso and submeso scale are an efficient transmitter of heat and material from the surface to the interior, because they can develop large vertical velocity. So mesoscale, we have the example, the Western Alborangay, close to here, and with it's like 200 kilometer radius, and a smaller structure from the submesoscale with 10 kilometers and very high Rossby number. This kind of structure in the vertical in the vertical spectrum diagram, we can see they can develop in a submesoscale model, develop important or relative important vertical velocity, like 1 order meter per day. But it's difficult to monitor this kind of vertical velocity. This is 3C experiment. In 2018, we published 2 companion papers about the frontal intensification in the Western Arbor and Gir and in the Almeria front. And then in 2018, we deployed SOTIP and script glider team deployed several gliders, and they published another article. And now I will present the result in the Balearic Sea. This is the area, the study. Now we changed in 2022, and we deploy glider, CTD cast, and this is a temporal evolution of satellite image to illustrate a multi-scale dynamic in the Balearic Sea. So we start in the beginning of the campaign with a dense front observed from satellites. It is surface temperature. So it's associated with a vortex dipole structure. It's like a mushroom structure, a warm mushroom, and decay to form or generated a small mesoscale cyclonic eddies that is propagated in the Balearic Sea. These have a typical 5 kilometer diameter. So what is a front? A front is characterized by a long jet separating dense and light water, and they have a cross-front circulation that produces subduction. And on the other hand, we have the submesoscale cyclonic eddy with a cold and large cyclonic vorticity in the core, and we have a welling in the core of the cell. So in the next slide, I will show the frontal intensification in the Balearic Sea and the cascade in the small submesoscale cyclonic eddies. So in SOCIP, we developed the Western Mediterranean Operational Ocean Circulation Model. It's a 2 kilometer resolution model, and we use in a forecast product to help to the planification of the Sea Calypso campaign, and then we produce a reanalysis product using the Calypso data to assimilate it in the WMOP. And finally, where I work more time, is developing a high resolution grid with 650 meters with 50 sigma level nested to the WMOP region. So this is an evaluation of the temperature in the Balearic front. This is from satellite, from model, and we capture well the position of the satellite, and then we capture the decay of the front and the production of the small submesoscale cyclonic eddies are a little bit offset from the domain. This is a movie of the Rossby number. The Rossby number is the vorticity normalized by the Coriolis effect, and we see that the front is intensified. In the border of the front, we found a generation of a small structure. This is another validation. This is a cross-section using a CTD from the Calypso experiment. And the model reproduces a vertical section of the temperature. The model reproduces well the position of the front, but it's colder than the observation. So we reproduce the intensification of the front, and this is the diagnostic from frontogenesis. We have a strong frontogenesis in the frontal area, and they develop across geostrophic secondary circulation. So we have a subduction and a welling. Now we examine the temporal evolution of relative vorticity and the displacement of parcel in the context of submesoscale eddy generation. So the front cascade produces a small submesoscale eddy, and in the right movie we see the displacement in the vorticity map. So we have the mesoscale front cascade to a forward small structure. And we have subduction in the periphery of the cyclonic eddy. So this is a snapshot from the movie. So we start, the parcel start to fix around the large cyclonic area, and we show a downwelling area. So the subduction is associated with a very large cyclonic vorticity. So this subduction is produced by a frontogenesis around the submesoscale cyclonic eddy. We found a converged large strength. The middle plot is the large strength. Produce a frontal tendency, a positive. The magenta pattern is tendency, and this creating submesoscale geostrophic circulary cells in the periphery of the cyclonic. And finally, the conclusion. So using the model and multi-platform experiment as Calypso, we can explore the intensification of the Balearic Sea front by frontogenesis on the 24th of February, then his cascade in a small submesoscale cyclonic eddy, developing subduction area in the periphery. And this movie is the 3D pathway and the vorticity, the vorticity. So we are in a very high submesoscale domain because we have a very high vorticity number, and we got in the periphery we have the subduction, an important subduction in like a spiral. We are creating a spiral from the deep layer. Thank you very much.
Gracias, Maximo. Thank you, Maximo. No, English. If you have few questions, one or two maximum, and short questions for Maximo. Vanessa, maybe? Yeah. Nicolaos, go.
Hi, Maximo. Thank you so much. How long do the edit split? How many days? When you saw this allocation and the spiral to separate in two smaller eddies?
Okay, this is a very submesoscale process, so it's like 1 week. So we start in 24th of February with a very intense front in the Balearic Sea, and they came faster. We have this is not the full story. There are a strong wind event, the created vorticity and created instability, and the front decay, and in a couple of days they start to generate the small structure, and the small structure stay coherent for 3 days, and they propagate it a little bit for the north, but it's very submesoscale event.
Thank you. Another question? So we will do the last presentation. We will postpone the presentation from Nicolaos after the coffee break, just to have time to listen to you correctly. Or, that okay for you? Yeah, okay, perfect. So, yes, Antonio Novellino, and you will do a presentation talking about EMODNet, and I think it's very important also for MonGOOS community.
Yes, of course. So,
why?
But, yes, of course, I will. I always. So thank you very much. Good afternoon, everybody. So my presentation will be the last one before the coffee, so I mean it's quite important to be in time and be clear. So what I would like to present you some programmatic data access of immanent physics for doing some studies for consuming data for doing, for example, extreme events application. But I take also the opportunity to just refresh a bit about what immanent physics is.
PDF.
No, tiene anche la PowerPoint se serve.
¿Lista? Sí. Para la pantalla completa.
Okay. Okay. So So I was saying, I mean, it's also a good opportunity to give some update about immanent. That, as many of you know, is one of, is a European program. So it is supposed to integrate and make available the in situ data. So, these days we are seeing many in situ data. Please make sure that your data end up in immanent physics, in immanent in general, because it's, a shopping windows for all the activities that we are doing. And this is a very recent infographics that has been designed by the Commission, and here you can see somehow the summary of the general idea behind the program. As I said, immanent is a program, is already targeting 2030, but there is also already a discussion, an ongoing discussion in order to see how to make the program evolving towards the next 10 years. immanent has been developed in a tier step approach, so we had several phases. Little by little we are integrating and updating both the dataset resolution and new products. It has been developed according to thematic projects, so we have the 7 thematic projects. I'm coordinating immanent physics, so I'm focusing more on immanent physics. And the idea is really to make the use and cooperate with all the existing network and infrastructure in order to elevate this data towards this, let's say, European picture of the data and serving many users, different stakeholders that could be European stakeholders, but also global stakeholders. Since January last year, we have reached a very important milestone because before that, each single immanent portal was a standing alone system somehow. Now, since January last year, all the different products and services have been centralized. So we have this central system that is presenting, a map viewer, a catalog, and you can discover all the resources that we have in the system. And as I mentioned before, for the Commission, immanent is the gateway for the in situ data in Europe and beyond. So please think about that when you're making available data. So try and see. Now let's go a bit deeper in physics. Modern physics is, as I said, is working on making in situ fair data and products. So it integrates both real-time operational data and delayed research data on ocean physics. We're working on common standard and tools. We had this morning a very important session about how to improve, some tools in order to, let's say, make a clear list of what we can include in the system. This is also some activities that we are running with the people. We have Francisco for Rivers, Begonia with Taigage. So, it's a common activity that we are trying to keep going. Immanent physics is dealing with, ocean physics parameters, so it's temperature, salinity. You have them all. Before, there was also it was mentioning also the importance of automatic weather station, and lately in physics we are also starting including automatic weather station because it's quite important information for modeling purposes, so they are start flowing into it, and there is an open action to this, so please help us in order to identify possible data sources in order to be integrated. These are somehow the raw numbers that you have. Actually, it's not very updated because I was checking the stats, and we have about 19,000 Argos, for example, that are directly interconnected via the Global Data Assembly Center of Argo. And again, it's quite important also the cooperation that we have with OceanOps in order to be synchronized with the metadata, because then we can really be sure that what we have in the system is exactly what has been planned to be deployed and is flowing into infrastructure. I have to say that it's quite easy, relatively easy for international programs in which we have, a trusted, let's say, inventory for the data. It is a bit more complex when we move to the national level, because we have many institutes that are not really sharing the amount of, the station, the platforms, the resources that they can offer, and so we may have some duplicates. In physics, we know we have some duplicates, but a constant work that we're doing is to really clean up this kind of problems, and again, we need also your support in order to do this. Physics is also a single point of shop for the Instituto data by means of the central portal, but it's also working on capacity building. So we are also helping out, the Secretariat and other, let's say, sister initiative in order to implement tools, training materials, and also code book, for example, to consume the data. And I will give you an example in a couple of minutes. We are also working quite a lot on improving, let's say, the linkage between the metadata that we are offering, some of the interface that Imonet is implementing, with the best practice, in particular with the Ocean Best Practice Initiative. Then, going to the system. As I said, we have the map viewer. This is the system, how it works. So in order to find the physics products, you need to select physics topic, and then under that you can see different themes that are the parameters. So you can explore them according, river outflow is one of them, or you can select all the Instituto data altogether. Usually when you access the system, you are, the system is presenting the stations that released at least one dataset during the past 7 days. Then in order to see more data, and of course if you interact with the station, you access to the data itself, so you can see, for example, the time series for a given parameter. In this case, I'm showing the outflow of the Po River. And then you can play, you have all the metadata and stuff like that. This is a simplified overview of the architecture. It's quite important to present this because based on this, then you can consume some of the services that Imonet in general, Imonet Physics in particular, is implementing. So this is somehow the general workflow that we are implementing. So we have sources for Instituto data. If the source is a trusted source, so it's one marine institute, then we have a direct connection. So we map the metadata, then we federate the data. Then according to the topology of the service that the institute is offering, we federate the data, in really federation, so we are just mapping the data, and when we have a request, we forward this to the original system. If the original source is not really implementing this kind of APIs, we need to buffer a bit some of the data in order to facilitate the data access, but we can replicate the request and we can provide statistics on that. We organize data in collections because we were asked to present data not by the platform, but by the parameters that they are collecting. So we had to reshuffle somehow the data in order to put together all the temperature data, all the salinity data, and blah, blah, blah. So that's why we are offering two main data sets. That is one related to the metadata, and one is related to the data. All these, information are made available by means of these 4 services. One is GeoServe that is supporting vectorial data, so it's also offering the maps that are loaded into the central portal. and CWMS that is supporting gridded data management and presentation, AirDAP for profiling, profile and time series, and GeoNetwork that is, the catalog in the end, and is just presenting all the other resources that we have in the system. How it works. So if you want to discover the data on top of the map viewer, you go to the map viewer, then you select, for example, the in situ data, then you can play. I'm sorry that they are very small, but you can access the presentation, so you will, you can see in detail. Then you can, if you want to extend the time resolution of the dataset that the station that are offered, then you have to go to the layers, then click on the icon with the filter, and then you can extend, you see in the top part of the slide, the time dimension of the slide. Then, if you select one specific station, as already shown, you see the features that has been collected by this station. So, in case of a river station, you have a time series of the outflow. In case of an Argo flow, you can see the profiles. So, actually, both the profiles, temperature, salinity, or if it's a bio-Argo, you can also see other features. And then you can already download the data directly from the web portal. So if you select download and then you download, then of course you get the NetCDF files related to that specific station. But as I said, usually you are not interested in just going there, download, let's select, download. If you need to do some more sophisticated, I would say, you need a programmatic data access. So in order to implement these services, you may you can exploit let's say, the AirDAP infrastructure, the AirDAP service. AirDAP is organized in a way that we are presenting the dataset in, let's say, very close to what we are presenting on the map viewer. So we have organized, we have set up a dedicated vocabulary that is the P33 that is mapping, let's say, the natural way we are telling the parameters, for example, carbon cycle or river outflow, into collection. This metadata collection is presenting the information about the station that has that specific group parameters and, some other metadata. For example, in case of salinity, salinity is also related to several inner description of the data. So, for example, salinity, you may collect salinity as a time series because you have a station, a fixed sensor, and then you get the time series, so you can collect it by profile. So we have two different data sets related to the salinity. Then, of course, salinity is not collected as an absolute value, so you may have the PSAL value, but you can also collect the conductivity or the sound velocity. So for each of them, then we have a specific metadata and data available in the infrastructure. But all of them are connected and linked. This is somehow, hopefully, a bit more clear, let's say, description of how this data is flowing. So now I'm focusing a bit more on river that is somehow easier because the river is the river outflow. So we have a P33 that is representing the concept, river, and then we have a P01 that is representing the feature, river outflow. We have two metadata dataset, you can see in this block. And the name of the dataset always refers to metadata. So if you see metadata, it's just metadata, and then you have the dataset. By exploring the metadata dataset, then you get the features, so the name of the stations, the location, how this feature is collected, time series in case of river outflow, and some more information about the parameters that you have. Then if you query the dataset, you access the real data. And the unique ID that is connecting the metadata dataset and the dataset is the name of the station, the code station that you can find in this. And the system is really working based on this because the central portal is populated by means of this information. So we are making available a GeoServer WMS service to show the position of the station that is made available by means of the metadata dataset that is organized by the P33. And then we are populating let's say, the platform page with the data that are retrieved, runtime retrieved by the dataset that is containing the data. So everything is synchronized, and so what you see, let's say, on the map viewer is exactly what you get from the AirDAP dataset. So you can really use this dataset in order to implement services. So first you can query, let's say, the metadata dataset to discover the capacity, and then you can work on the specific dataset in order to collect the data. Then here I just added the 3 pictures to show how I did in order to identify one station very close to the Po River mouth. And this is the few lines. I mean, I wrote some Python lines in order to retrieve this data, because AirDAP is also exposing. I mean, AirDAP is a very powerful tool. I don't know if you know it. If you don't, I mean, we can talk about that later. It offers, the very convenient fact that you can expose data in different data formats. So, for example, here I'm calling the CSV answer of the dataset. So I'm collecting the Po River outflow information as a CSV. So I'm parsing them with, some Python scripts. And with a few more lines, I can already plot, the feature, so the outflow. But why it's so nice and so important? Because, okay, we are speaking about programmatic datasets to see stream events. Po River, this year, we had a number of floodings. So the idea was, okay, let me try and see if I can spot an easy way to identify, triggering events, or a kind of way to see if, by means of the, this programmatic playing with the data that we have in physics, I can identify some of the major events that we recorded. Here you have the events. We had some events. You see the errors. I don't go for them. So the idea was, okay, let's try and see. Okay, I do a weekly flow average in order to have the average outflow for that period. Then we do a peak amplification, because of course if we have flooding, we have an increase of the outflow. And we just play with that. And then we clean the peak, because I'm only interested in these spikes. So by just playing with the these few lines of code and stuff like that, I was able to identify these peaks that are exactly mapping the events that have been presented by newspapers, and and people that are living on that side of Italy were experiencing that. And so the conclusion is that these days we are speaking about extreme events, and they are including atmospheric heat waves, storms, strong winds, strong rainfalls, floodings, sea level, temperature changes. In IMONET, we are already integrating many of these data, and we organize the data in a way that can be easily consumed by each and every one. I just showed a couple of examples. And by means of this physical AirDAP instance, you can really consume and do application that can detect or predict extreme events. So IMONET is open and free. It's up to, it's for you, it's for us. So once again, it's quite important also to make available all the data that we are collecting into this infrastructure, because having them in this system means that then we can implement new services, we added value services on top of that. I just put also a picture, because you can apply the same concept to sea level. And you just change one line of the code, and that's it.
Thank you very much, Antonio. I think it was a very clear presentation on MonGOOS. Do we have any question in the room? Catherine? Yeah, let's go. Yeah. You need a microphone? Because you have a small room.
Thank you for the presentation. I was wondering about the BGC Argo data. Where are they going to? MonGOOS chemistry, or are they in MonGOOS physics?
You can find them in, this is somehow a bit difference between IMONET physics and chemistry, because chemistry is consuming operational data or in situ data to make available products that are serving some specific, let's say, stakeholders. For example, they are serving quite a lot the Marine Strategy Framework Directive products. For the operational data, also the BG Argo, you can find them in physics. Actually, we lately made them available. So you can find a specific data set with all the BGC Argo in physics.
In both.
and air data.
Because the same happens with the ship data, where you have the physical part and you have bottle data, which are kind of split. So sometimes it's important to have the two together. So when I download data for bottle data on MonGOOS chemistry, then I have no way to find a corresponding CTD cast in MonGOOS physics, so I don't know if you
we are working on that, yes.
Okay.
For example, also for CTDs, at the moment you can find there is once again, there is a specific data set that is including something like 5 million CTDs. That, again, it's including many CTDs coming from Pangea, from ICES, and there is, it's not fully synchronized with the CTDs that we have in Copernicus Instituto, because the problem of caching and synchronizing the stuff. But little by little, we are trying to make everything available in physics, so you can discover the resource there. I didn't say, but of course, I mean, it's quite important, the collaboration that we have with Copernicus Instituto, because we are really working together in order to make, I mean, all the data available in both the systems. Of course, I mean, there are some little differences because, I mean, the main focus for Copernicus is serving the Copernicus, let's say, community, and in physics, in IMONET, we are also adding some other data that do not reach the same level of quality that should have in order to be consumed by the Copernicus community. So you have somehow a wider, quantity of data in physics, but we are trying to clean this data in order to be included also in the other one. And so it's a very discovery opportunity to work with, to play with the IMONET physics, for example.
Okay, thank you.
Of course, we have time. No, no, we don't have time. We have to go upstairs, but... Can you ask your question during the coffee? Yes.
Ask the question and answer.
Okay, so let's have the question after if you want for you. Antonio, I take the opportunity to have you with me. I discuss a lot with the community. Empezamos de nuevo, Vanessa. Gracias. I hope you had a good coffee break. We decided to have the question for Antonio now, so I hope you didn't forget the presentation and your questions. Vanessa, maybe you want to start, because I remember you had a question.
I already discussed with Antonio, but there is, we can share what I ask is how linked are EMONET with OceanOps? Because our dashboard is more related with OceanOps, I wanted to know how much is related, I mean, about sharing the information among the two data aggregators, because there was one of my figure that I was showing about the competition, complexity, disaggregation, and very quickly.
No, yeah, I think it's an important point. I also had a discussion with Antonio on the, yes.
So you can answer.
No, you will answer.
No.
But I think, yes, just to explain people, because I think not only Vanessa and I are wondering about duplicate efforts, and so yes, please, Antonio.
No, well, actually the system is very well synchronized because we are harvesting all the metadata, especially for the international programs from OceanOps. So we clean the metadata with the information that we harvest from the APIs from OceanOps. So that is quite important for us, because then we can guarantee avoiding duplicates in some of the platforms that we have. For example, in case of Argo, drifting buoys, or other, I mean, ocean gliders, for example, also. That is not a very good example, because gliders, we have much more than what we see, actually. But for Argos, for Argo and the drifters, we ensure that what is deployed is exactly what we get in physics, because we can use OceanOps as an inventory for this. As I also mentioned yesterday while we were discussing, there is a problem when we start moving at the national level, because we have not, let's say, an official inventory of the stations that we have to, we can refer to. So if we can set up that at MonGOOS level, then it could be our trusted, let's say, inventory for knowing the station. Then if we get new station, we add them, and then we can check that this data is available also in physics and other station. That is a part. We are doing the same exercise with sea level. That is much more complex, because we are heritating a situation that is coming from other programs, long historical, elderly programs. But little by little, we are also going to that direction. So we need to have this kind of trusted inventories, and OceanOps for sure is one of them.
Yeah, and I don't know where is Manolo. Here. But yes, we try to do this inventory for the measurement and see it's complex. I think the future is also to have machine-to-machine communication between all the system, to avoid people to do manually many times the same thing. So we have to work on that to be able to, even in MonGOOS dashboard, to be able to communicate directly with the other data aggregator, data center, metadata.
Absolutely. As we were saying, I mean, this is a very important point, because we need to avoid, of course, duplication of effort, especially to submit metadata and data. So we need to know that all the systems are synchronized. So we need to tell all the people that this is working, and we need to work on the pieces of the story that are not working, because we need to solve them. And then, of course, yes, it's important then also to facilitate the data release of the data. We were discussing before. I mean, the first point is to make this inventory, so have the metadata of the platform. Second point, attached to the metadata, is where the data is, because we can, in order to implement services like the one that I briefly presented, we need to access data. So together with metadata, we need to also to have the endpoint where we can access and federate the data. And again, interoperability and tools like AirDAP and others that are coming out are important in order to make it in practice.
Yeah, you Nicolas, and I think there is also a question from you.
Sorry, just a very quick question. So if I'm a user, from the user perspective, and I'm going to EMONET and download the data today, okay, for all the Argos, are going to be a different version of the quality of the data if I download 3 months after? if someone, if the Argo community release more,
Maybe I can answer for Argo if you want, but yeah.
Because we are synchronized with them.
I know quite well the Argo system, and Argo indeed have a strong data system. You have real-time data delivery with basic quality control, and this real-time data will never change.
And this is what you get in physics?
Never change, but you have a delayed mode data that is updated after, depending on the parameter, but 2 years, 1 year, whatever you want, and this
is not coming yet. Okay. At the moment, we are only connecting the operational one.
The operational, okay, thank you so much.
That is also, but you raised a very good point, because somehow we also need to clarify, let's say the different, it's not version, but it's the quality that you apply to data. And we have a very good example from sea level again, because if you look at the University of Hawaii Sea Level Center, they are releasing 2 different data sets. One is, let's say, the operational one, and one is research purpose one. Maybe we need to start working on that kind of concept as well. In IMONET, at least in physics, this is not started yet, but it's a good feedback, a good point to work on.
Begonia, let's try to be quick. No, we have time, we have time. But try to be quick, because after we have a question from you, you can, and after we can switch.
Yeah, that's very quick. I think you already mentioned, but it's important to emphasize that whatever we do in general, in the specific networks, in the programs, is that we must ensure a coordination, because otherwise, and now I have the hat of data provider, you are filling service every year, different service, and metadata is really a very important information, so it's a very important job. This collaboration is really ensured. And also with respect to the quality of the data, in Copernicus we have a sea-level reprocessed data, which is a delay mode with quality control, blah, 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 and this has to be explained. Yeah, it depends on the data portal. You have different types of data with for different purposes.
Again, it's quite important to put this information in a document that is attached to the metadata. Then it's up to the user to decide which is the kind of data that they want or they want to use.
Maybe because he's waiting. No, let's go. Go.
Very impressive work for the user. Do you do some work for the data provider? So what do you offer to the data provider?
For the data provider, actually, is the visibility. That is a key point, because again, it's one. Yes, but now, I know it's little. Well, actually, there is also some feedback loop with some information. When we do some harmonization in metadata, we correct things. We also inform the providers that some data have issues. This is always done. And this is also in collaboration with Copernicus. It's massive activity. But the very most important value is really the visibility that you have as a provider at the European level, because, as I said, IMONET and Copernicus are the 2 main programs from the Commission to observe the environment in general and the marine system. So having your data in that is also fulfilling some assessment that you have to provide, because if you need to show that you're feeding the system, so if you are sharing data, if you are you really fair compliant? If your data is ending up in physics, in IMONET, you can tick it off. So it's also a kind of KPI for your activities. At national level, are you sharing your data towards European and global initiative? If your data is ending up in IMONET, you're proving that you're really doing, it is really the case, because you are setting up all the kind of metadata models, API interfaces, tools, standards, blah, 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 that is enabling this kind of thing. So it's sort of proof of that you are doing properly in your work.
Yes, and you can report at the European level also
yes,
the contribution. It's a way also to make visibility, but also to advocate for your work. And I would like also to add that it is sometimes compulsory for many projects, European projects, for example, you have to share the data. Yeah. So,
if you think about the Horizon Europe project,
no, we have to go. Okay.
It is compulsory to share the data to make it. work towards the interoperability towards IMONET and Copernicus. So that is a KPI assessment, really. It is, obligatory from the Commission. So for European parties, this is a kind of...
Okay, just last quick question, George. And,
if it is operational, yes. If it is delayed mode, we need to harvest. It's not immediately, but we are working also to better synchronize the two systems.
okay, thank you very much, Antonio. But
I'm there.
that's why I say that the presentation is important. Yeah, many questions. Okay, so next speaker, please, Nikolaos from SOCIB. ADs, we are talking about ADs and gliders again.
Yeah.
Thank you.
Sorry. Good afternoon, everyone. First of all, I would like to thank the great opportunity to be here with all of you. It's the first time both in Malaga and both in MonGOOS. So today I'm going to talk about the work that we did a couple of years ago with the Calypso project. Already a few things have been mentioned from Maximo, but this time I will focus more on the gliders. So here, as you can see, we start with a large-scale survey, and that it was to support the ship operations. So we had 2 long lines along and across the channel. And after that, we deploy 6 additional gliders, and all together, they work, 8 gliders together, they work together to resolve what we call small-scale repeatable surveys that it takes place every 3.5 days. So these gliders were apart every 15 kilometers, 4x4, and every 4 hours they sent a profile. So every 5 days we have, if you think in a little cube, okay, 250 profiles, okay? So the initial focus of this survey was a cyclonic eddy that was observed from a float. So we used the exist observations in the sea, and then we sent all the gliders there, okay? So on the large-scale survey, what we observed, it was, as you can see on the top panel, here we have a cyclonic eddy that was detected also from SST and absolute dynamic topography, and then we cross that and we see clearly the size of this mesoscale, let's say, eddy, and how deep it penetrates. In addition, Maximus also talked before for the filament that allocate, and we see clearly that extend vertically 50 meters. We see enhancement of the chlorophyll on the frontal area, and then a subduction of the chlorophyll below the photic zone. So here the subduction, and I keep that, we will discuss about this point later. Here the subduction starts from the surface, from the mixed layer, okay? So on the small scale survey now, we combine all the data, and pretty much it's like having a survey that it is equivalent to 3.8 knots. So we objective map this data with 50 kilometers across front and along front with a time scale of 7 days and vertically every 10 meters. And we create a grid of 2.5 kilometers of observations now. So then we potentially constrain this to be statical stable. We resolve the QG omega equation, and we interpolate to the potential density surface. So now, here we are moving to an animation, but that is from observations. So this is glider observations that they have graded onto 88.9 isopycnal. And what I'm showing on the right side is the salinity, and on the other is the depth. And what we managed to do is actually we are able to resolve the evolution of the eddy field in the Balearic Sea. So we capsule several phenomena that they take part, and I will focus more on the eddy merging and the eddy splitting. But on the table you could see this evolution, what I consider that it's important, and some general characteristics of that isopycnal that we use. We saw that the mean depth of this isopycnal, it was 110 meters. The temperature it was 15.5, the salinity 38.3, and we saw excursion of the 28.9 isopycnal up to 100 meters, okay? The survey, after the Slocum gliders that they recovered, it was moved to the northern part, because we are targeting for features, for mesoscale features in the sea. And the gliders, they have, the spray gliders, they have ADCP, so we are able to calculate the potential vorticity and relative vorticity. So we saw the Rossby number that it's up during the period, the observation period of 0.5. Also, we saw that it was observed when the cyclonic eddy formate, followed by eddy split on the 2nd of May, that we give more details later. And the high potential vorticity was observed on 28.9, so below the mixed layer. So we are able to resolve the omega equation, as you can see on the animation, but now I'm focusing for the eddy merging and eddy splitting. On the top is before the event, before the eddy merging, and below is during the eddy merging, and we see that the vertical velocity has been changed rapidly in a period of 2 days. And we saw also areas that we have photogenesis that we are going to talk a little bit on the next slide. If it is allowed me, yes. So now we try to examine how these vertical velocities, they have been developed. So photogenesis observed on the west edge of the cyclonic eddy. We talked earlier that photogenesis most of the time on the cyclonic eddies are on the periphery where we have ageostrophic velocity. In addition, on the top we have the redistribution of the potential vorticity of that isopycnal that we see at degrees of the PV after the eddy has been merged. And on the bottom, we have used the advected frontal tendency and the relative vorticity. And why we use the advected frontal tendency? Because it's an indication of where we have photogenesis and photolysis. So we can see that on the isopycnal bell shape of the 28.9, sorry, we could see that an enhancement of the photogenesis there. But how we can link that with the ecosystem? What is the impact for the ecosystem? And here is the vertical sections of the chlorophyll and acoustic backscatter from the ADCP, which can be an indicator of the zooplankton, as Laurent mentioned before. So we can see that the vertical velocity, downward vertical velocity has been developed where we have the photogenesis, and we see the subduction event take place at that moment. But I will go a little bit further. Okay, we try to understand also with observations now, with the glider observations, how the mean kinetic energy and eddy kinetic energy change. And we see that, so I have 3 phases here. I have before the eddy merging, during the eddy merging, and after the eddy merging of that specific isopycnal that we have targeted, the 28.9. So during the eddy merging, the mean kinetic energy was redistributed on the study area, on this small cubic that we have, and the eddy kinetic energy within the merged eddy has been indicated in backward energy cascade. Okay, so I'm leaving now from the eddy merging, and I'm going to eddy splitting. So here you see that the cyclonic eddy from the positive relative vorticity and the depth is allocated, and it's split into smaller cyclonic eddies that we see on the bottom plots that they in 5 days. So we are talking for phenomena that they are very rapid in a time scale of 1 week, okay? And this cyclonic, the new form cyclonic eddies are around 15 kilometers okay, and we saw that the isopycnal depth dropped from 100 meters to 50 meters. And they had this in the Balearic Sea. Normally, on that period, they are surviving for a couple of weeks, okay? So now, what is the impact now of the, we are going again to the impact of the eddy splitting now to the ecosystem, okay? So we saw that the PV has been decreased and the vertical velocities have been increased. So this time we add vertical transport of the system. And we are able to observe subduction now, not so good from the chlorophyll, but from the acoustic backscatter. Okay, and we try now to link that with the Lagrangian from the models. Okay, so here on the top is the trajectories of surface particles, and on the red circle is where we saw the cyclonic eddy at the beginning of the survey when we did the large-scale survey. So we saw that the particles, they start subduct from the 2 meters. So we initiate the particles at 2 meters and they go deep to 50 meters, which is very well correlated with the observation. But now, if we are going a few months later, that the stratification has built it up, and then on the small scale survey, we saw that the subduction take place below the mixed layer depth, okay? We saw that we need to initiate these particles to 50 meters to be able to resolve the subduction events. So it's how you approach between the different, the different seasons and the period and be able to resolve when you are going to have subduction event. And we are in a good correlation. Here is, again, a specific day from the glider work with the WMOP that we're using that has been assimilate the glider data. So we see that we are in a good correlation overall. You know, the model do quite well from the depth of the 28.9 isopycnal of the vorticity, and on the vertical velocities, we are on the same magnitude, 25 meters per day. Okay, and now to conclude, we saw that the glider network gave us a better understanding of the eddy field. We are actually the strength of the gliders is that you are able to leave them outside for a long time. So with that way, you can wait and see the evolution of features that you are able to detect. So in our case, we target at the beginning an eddy and then we moved, but actually, we saw all the evolution of the eddy field for a period of almost 3 months. We are able to describe and analyze the eddy formation, decay, merging, splitting, and also we saw how the biochemical distribution changed for the ecosystem. So the eddy field also allowed us, it gave us an enhancement of the productivity. And I will close here and just quickly to mention that this period, in parallel with the Aquarius project that we have also our SOSIP competitive access that it's open, and we offer our gliders for 100 days. You can use the barcode and use the proposal, okay? You know, you can submit proposal to us. We are happy to answer. Thank you.
Thank you very much, Nikolaos. We have time just for one question because we are very late. Nobody? We can discuss later together. Okay, so the next speaker, it's Martin, and we will talk about, let me see, real-time observation for. Yes, I think so. I hope so. If you are ready.
Oh, well.
Okay.
Let's see.
Let's see your presentation. I was not able to say your names, so I prefer to call you Martin. Is good. Van Fulken, that's you.
You do that very, very well.
Yeah?
I can make it German speaker.
Yeah. You have German?
floor is yours. It's your presentation, yes?
Yeah.
Yes, okay. So it will appear in full screen here.
It's okay.
No, thank you.
Okay. Thanks for giving me the chance to tell you something about the Northern Adriatic and what we measure there. I'm coming from the Center for Marine Research. Sorry? Yeah, but I mean, it's very close, right? Almost here, there. Left and right of Italy. Center for Marine Research in the Northern Adriatic, we're doing ecosystem approaches towards the Northern Adriatic. We want to understand how it works as a whole. Very biologically oriented for the last 133 years, and what we normally do is ship-based oceanography. So this is not going very well, but let's keep it. So those are the, we have a few stations in white. Those are the stations that we try to visit monthly, and of course we end up not visiting them monthly, as you said already. So it's up to 8 times a year approximately, and with climate changes this is a decreasing number, unfortunately. You probably all know this all these classic approaches. What you see down here are the stations that we visit a little bit more frequently, a little bit more safely. Those are part of our national marine monitoring programs, where we get most of our ship time from. This is what it looks like, and why we do it. We do that in the Northern Adriatic because it is a very shallow area, and it is a sea area that you can actually, we think at least, can get a grip on. It's not so deep, 30-40 meters max. And you will later hear something about the importance of the Northern Adriatic in the formation of cold and high salinity deep water. And also you see how it loses its importance in that particular process. So I'm not going too deep into that to make up a little bit for time, and we go to the next part. So what we do normally, we started with physical oceanography some 133 years ago. Then somewhere in the 70s, we became very, very systematic. So it was not sporadic ocean observations and habitat mappings and biodiversity surveys, but then it became a systematic approach to the Northern Adriatic Sea, and then we added a lot of microscopy for biological parameters. That was very interesting. It went up to physiological measurements that we added on top of that oceanography, all the time keeping the general setup of the sampling. So we are still sampling across the entire Northern Adriatic as much as we are allowed to, and try to understand the entire system, right? So we are just adding parameters and adding experiments to that. Then we saw that we need to step into this molecular world and add meta-barcoding and meta-transcriptomics to all that measurements. And as you can see, this is something of an exponential growth of effort, costs, and data flow and data volume, basically. And for the last 20 years, we're working on the automatization of that and on making the entire portfolio basically operational. So we want to have all this data ready to produce a digital twin. That's what the overall idea is. And for that, we have a very old database. It started in Paradox. I don't see that old people here in the audience that remember Paradox. Does anyone remember Paradox? So sorry. Okay. Today it's a MySQL database, and the interesting thing for you maybe is that it's one database in which we have the complete portfolio from physics, chemistry, biodiversity, molecular data. That becomes very, very complex and very, very high dimensional, and everything is collapsing or congregating back onto one primary key. So for the database people, it's very easy to map that back on an AirDAP server and send it back. So what we're really searching for right at the moment is a way to keep the complexity and keep the primary key, because as we heard, one of the problems is you have bottle data, you have temperature data and you can't get it together, and then if you want the CTD data, you have to search in the third place. In our database, you do not have to do that. Of course, we have a dashboard for that, and we have users that are accessing that. And in front of that background, we now stepped into further automatization. So we have a small laboratory installed on a buoy that's like a 24-ton buoy that is floating. There's one a mile out in the Adriatic and in northern Adriatic, and there's one 6 miles out in the Adriatic. We're measuring everything that we can afford to measure automatically, and the interesting part of that is that we add a lot of biological measurements on top of that. So the most complex thing of which is that we ultimately can retrieve direct data is something which is called imaging flow cytometry. We heard the Darwin, no, it was not Darwin, what was called the automatic picture analysis that you had. Who had that? All right, exactly that one. So we have a very similar system for that. So you need basically a training set on which you can map all the new pictures that you get. On top of that, you get the analysis of chlorophyll per cell and all the other pigments that you have per cell, and can say something about the physiological state of those phytoplankton cells. In this case, we are mainly interested in phytoplankton. That's where we're strongest. And we add that on the data set, and then we complicate it a little bit more because we thought that we have to make the system slightly intelligent, not too intelligent, just slightly. And what we what we did for that is we made it what we call self-aware. So everything the buoy measures is some parts of the things that the buoy, some parts of the parameters that the buoy measures are analyzed directly on board. And if we find peaks, if we find steep changes in chlorophyll, for example, we can trigger a process downstream. All of the data is sent to our server. Yeah, you see our server there. Where the data is put into context with historical data. We have something like 14 million data points for the Northern Adriatic for the last 40 years digitalized in there. And we put it into that context. So if we see a certain peak coming up, like for example the spring bloom in chlorophyll, we can trigger downstream process. That information goes back to the buoy and changes the sampling program. For example, we initiate a higher frequency of sampling for the imaging flow cytometry if we see a bloom coming up, or let's say a cloud of phytoplankton floating through, because that is in most cases rather the case than a bloom. That information all again is gathered back. Some of it, the ones that is interested for fisheries, that's why I thought it might fit into this workshop or into this installation of the MonGOOS meeting. Most of the data that is interesting for the fisheries is sent via AIS on message 8 out when it works, and received by the fisheries fleet, and they can use it for their work, either to find fish or to know when they have to go out, or to know when they do not have to go out. So they use it for their operations, basically. There's early warning systems involved or not, but that is basically based on their own appreciation of the data at the moment. And we can have an auto sampler. That is something that we're at the moment just getting to work to trigger a sampling event of seawater based on the other parameters that we measure, and use those samples later on. That is very, very delayed mode for the extraction of DNA and RNA and extract metabarcodes and metatranscriptomes from that. So it works, but it's not really completely operational. All of that is remotely accessible, so a user can remotely access that and change the program, interact with the sensors, and compare it with their own sensors that might be involved. We have quite a few sensor producers that are comparing their sensors to what we have at the moment installed there.
now maybe a little bit more something fun. So that was the observing system that we have here. We are trying to, by the way, integrate that with the system of the DHMZ that Diana explained us about, or told us about a little bit earlier. And what we had now this year, as we are talking in this workshop about extreme events, we had an event which is called mucilagine. It's a lot of polysaccharide mucus aggregations. Basically what happens, at some point there's a phytoplankton bloom, then they run out of some essential nutrient, and the only thing that they can do is produce sugars and excrete the sugars, and those sugars are then aggregating in the environment. You see that here on the left-hand side. This is an early stage. At some point this is going to float up. This is accumulating all kinds of sticky things in itself, and what you see on the right-hand side is a very late state when you have huge aggregations, 2-3 meters, that at some point fall down on the ocean floor. So that's the entire cycle. What it triggered, and that is maybe the beauty of the system that we installed now, is we can actually foresee an event like that. It's very difficult to show that. You can see here in the beginning there was a phytoplankton bloom with a chlorophyll maximum, and what we also see is a sharp and early increase in temperature and a sharp decrease in salinity. That is the river Po that floated the entire northern Adriatic and reached the other side, the Croatian part. You see that here? That is the corresponding chlorophyll picture. That happened early in the year. At some point that triggered a chlorophyll containing, first of all, a chlorophyll containing a phytoplankton bloom. Those cells, phytoplankton cells, couldn't grow any further, had to lose their chlorophyll and produce a lot of sugars. And then we had basically all the polysaccharides that were produced floating around in the northern Adriatic from July to the end of August, early September. Because, and this is something that you see down here, the meteorological conditions, basically the wind, kept all the water in the northern Adriatic, at least all the surface water. And nothing was going out of the northern Adriatic. It was somehow staying there. That is something that you will probably see this year in the South Adriatic pit. It has to arrive there at some point. And this is not going to be beautiful there, I think. To do all that, you need some people. Those are the people that are working on the buoy and try to gather all the data and keep the data flowing, which is Sisyphus work, I can tell you. With that, I close and hope we have some time left. Or we have some more question time.
If you have questions for Martin, thank you for the presentation.
Please.
Thank you for the presentation. Can I speak? Yes, you can. Take the mic. Okay, thank you.
Thank you for your presentation. Do you register any drop in oxygen after mucilagine event?
Yeah, this is, in the beginning, there's a lot of oxygen around. Sorry, in the beginning, there's a lot of oxygen around. Then there's a lack of grazing. So a prerequisite of mucilagine forming is that there's no grazing. And afterwards, there's also no bacterial deterioration of material. So basically, no one can use up the oxygen. So the oxygen, it's not as high as it should be, but it's also not really dropping. All right. And the real drop comes when everything falls down and covers the ground, and there it's there's this internal nutrient release from the sea bottom at some point at the end of the year, and that comes together with a lot of this sugar around, then there's going to be a lot of respiration in the bottom. So then you'll have bottom anoxia if you have it. If it stays in the northern Adriatic, if it goes somewhere else, you'll have it there.
Thank you, Martin. Other question for Martin?
take this one.
I have here one, right? I can use that. Yeah, that's everything.
Thank you for the presentation. My question is not so physics, it's more in biology. Have you discovered what is the responsible of this kind of aggregates? What kind of phytoplankton?
Yes, it's not an easy answer, right?
It's the diatom.
In our case, it's the diatoms. It's not everywhere the diatoms. It's always primary producers. It can be dinoflagellates, and it can be also a succession of diatoms and dinoflagellates, even though succession is very rarely the case. It's different species of diatoms. It's not always the same.
Yeah, because it's happened something similar in Canary Islands in the south, but with cyanobacteria, with trichodesmin, so probably it's different species, yeah. Thank you.
Thank you for the question. Other one? Short one? Very short one. Thank you, Elena.
Thank you. Very beautiful presentation, and I want to ask you if these data are available or belong to any data portal or something like that?
Yes, this data is available for all the users of our database.
Okay.
Maybe I explain that a little bit further. It's not in EMODNet. 2 reasons. Not all data authors are comfortable with sharing data. The second reason, we are not yet completely comfortable with giving up the complexity of the data and splitting everything up. But it's going to happen in the near future.
Okay. Okay.
Underneath the data, it's okay? Yeah. You share it? No, but you're happy to get it.
Okay, thank you. Thank you very much, Martin. Thank you. Next presentation will be from Begoña Pérez Gomez, and without any surprise, we will talk about sea level rise.
No surprise, okay. So, good evening, practically everybody. Well, for those that who don't know me, I am Begoña Pérez Gómez. I work in Puertos del Estado, and I will focus the presentation today on presenting some preliminary results about evaluation of the sea level rise and vertical land movement in the Spanish ports. So I will focus in a very specific climate hazard, and also in relation to the presentations we already had this morning by Pablo and Mark about our need to prepare our ports and start thinking of the climate change observatory and the adaptation strategies. So I will focus on a very specific problem, and I want to present this preliminary data, our studies we are accomplishing in collaboration with the SONAL and the University of La Rochelle team. Okay, I will explain later. So rising sea levels are one of the most significant climate hazards, which have potential impacts on port operations due to more frequent flooding, more frequent overtopping, as the events we could see this morning in Melilla presented by Pablo. It can have impacts in the operations of the port, for example, due to flooding of the roads. Also, we may have problems in the navigation in inner ports, and with the maneuverability of big ships when the tidal range also increased due to sea level rise in some cases, especially during the extreme low waters. And it has impact also in the infrastructures. Structural damage, erosion in the infrastructure support, and mainly sometimes related to this increased frequency of the impacts generated by big storms due to the fact that the baseline, the sea level, is slowly, progressively, rising. So sometimes this is difficult to communicate because we are talking here about a process that changes with magnitudes of the order of millimeters per year. So this is important to take into account. We are focusing on the long-term evolution of mean sea level. I have a video here, let's see if it works, that mean sea level rise can also generate what it's now usually called as chronic flooding in the literature. Even in the conditions of very good weather, calm weather, you can have these flooding effects during very extreme spring tides, like the ones we experienced 1 week ago, at around the 18th of September, and that caused this kind of situations in many ports. This is an example of a video I received from La Carraca port in Cádiz, just 1 week ago. So all these risks can be exacerbated, and is well known, by local and coastal subsidence. Then we need not only to measure sea level, but also to measure land movements. So we decided to make this analysis to understand if we have enough information, detailed information, about subsidence and vertical land movements. Normally this is not an easy to find type of data. They are not generally provided operationally in data portals. And we wonder if it can impact detailed risk analysis within a port, because we have to prepare the ports and the adaptation plans based on an inventory of infrastructures and operations. And are we really measuring adequately this hazard, taking into account spatial variation of vertical land movements? So that's the main motivation of this exercise we are starting with La Rochelle. Okay, so of the study for the Spanish ports will be focused on the Red Mar network, which is a network of tide gauges operating since 1992, composed nowadays of 41 stations. I want to emphasize that this network is a modern network in terms of sea level. Most of the sea level networks in the world, in many countries, have, fortunately, in many cases, even 100 years of data, which is easier to monitor long-term sea level evolutions, of course. In Spain, these stations are run by the Spanish Institute of Oceanography, for the Geographic Institute. So our network is very modern. However, it started in 1992, and now we have more than 32 years of data in at least 14 of these 41 stations. So that's why we are starting this detailed assessment of long-term evolution of sea level. This is the distribution of the stations. I want to emphasize that we have focused over the years in one of the main objectives in Puertos del Estado, which is contribution and integration in operational oceanography and early warning. And this is a key element also of the adaptation to climate change. I could say, okay, that part of the work is done in Puertos del Estado. We have done that well. We have automatic alerts when there is a sea level over a specific threshold. We receive immediately red alerts or orange alerts with the sea level and wave information, not only with this network, with all the systems we have implemented with other type of variables. So we have done a good job building this operational network integrated in early warning systems, including in our storm surge forecasting system, and also we share our data even for tsunami warning. So again, our concern and the objective of this job is the network ready for an operational precise assessment of long-term trends, and talking again about millimeters per year, which are the uncertainties that you will see there are many that can be accepted in order to prepare for adaptation, which are the level of details required by the ports. I want to emphasize that we, in order to measure vertical land movements, we have established, following the Global Sea Level Observing System recommendations several decades ago, a permanent GNSS receiver to measure vertical land movement at least 10 of these stations. But these time series are short, and this data need to be integrated in our system, and especially not only for operational early warning, but also for informing adequately decision makers about trends. Because one of the problems we face is that we must be able to understand and monitor the slow trends of the key variables, and sea level is one of them. So I will start just showing some key facts based on recent analysis of the data we have made in our team in Puertos del Estado recently. If we want to know what is going on, we have very short time series, of course. We have altimetry data nearby our ports where we can find relative absolute sea level near our coast based on altimetry, and we have the relative sea level to land provided by our tide gauges. Based on this, we have now, as I said, more than 32 years of data, starting in 1993 that, well, it's a good coincidence. It coincides with the altimetry era. So we decided to start this detailed analysis comparing data with altimetry, something that we already tried 10 years ago, but now we have more data, and this kind of studies makes more sense as the time series gets longer. We find, of course, we have now relative sea level trends in our tide gauges that range, the spatial variability range from 1 to 5 millimeters per year, depending on the station. We would like to understand which is the reason of these diverse trends we are observing. 5 millimeters per year, for example, is the trend we observed in Barcelona. As we will show later, that would imply that the mean sea level has risen about 15 centimeters since 1993 in Barcelona. Is this a real trend, local trend? This is the kind of things we are trying to understand, okay? And assess the spatial variability and understand the contribution of vertical land movements. In this analysis of our sea level in the Spanish ports based on the RedMar network, this is a workshop that is also about streams. This is not focused on the kind of streams like the Melilla event with waves, but it's important that probably you are aware, if you go to the NASA website, you can see that 2023 beat a lot of climate records, and one of them was the sea level. They detected a sudden jump between 2022 and 2023 related to a very strong El Niño event that boosted the effect of sea level rise due to the warming and the melting of glaciers and island sheets. So we decided to check what is going on in our ports, and yes, we found that 2023 was the year where we recorded the highest mean sea level. These are annual means in many ports in Spain. Here we can see the stations in the Bay of Biscay, in Galicia, where we recorded the maximum practically in all the stations, with anomalies with respect to the mean reaching 95 millimeters in the port of La Coruña in the north of Spain. And most of the ports in the north part of Spain reached the highest value in the history of the tide gauge in 2023. This is the same type of plot for the Mediterranean and the Balearic Islands. I will not show the Canary Islands, which are similar to the Bay of Biscay. In the Iberia-Mediterranean coast, however, it was not a record, but it was a record in most of the Balearic Island tide gauges, for example. With an annual mean increase of up to 54 millimeters in Mallorca, in Palma Port. So this is a fact. This is more or less coherent with this peak in 2023. And as I was talking with Christian yesterday and today, we found that you can see here the averages of the monthly values in Santander as an example in blue for the period 1993 to 2022. And in red, you can see the monthly means in 2023. And you can see that this mean sea level was over the mean. There was an anomaly that was present during several months in 2023, reaching up to 15 centimeters above mean sea level in November, which is in the range of magnitude of the seasonal cycles. And this is similar in other tide gauges. So in order to, there is a problem in the slide, okay, it's okay. So as I said, we started this first study, just preliminary ideas that I will share with you today. with the University of La Rochelle, which is the team in the University of La Rochelle participated in the SONEL data portal. SONEL is the Global Sea Level Observing System data portal that integrates vertical land movement information, the GNSS data information from all stations around the globe in order to measure vertical land movement with in situ data. It's one of GLOS official data portals. We have worked with them for many years, and we know that there is a demand nowadays of providing sea level data corrected by vertical land motion. And there is an increasing number of stations, tide gauges that are collocating a GNSS in the tide gauge, as we have started to do in recent years in the Red Mar network. So now we have to see how we can use this information to improve the products we provide in relation to sea level. Apart from that, in this study, we are going to use, of course, the GNSS in situ data, which is this permanent receiver installed on top of the tide gauge that will provide us the vertical movement of the station. And we can use also the tide gauge. Of course, these are the two more precise information we can have, but it's a very local, and it's just a point information. On the other hand, we will also recover the periodic leveling campaigns we perform regularly in the Red Mar network between the tide gauge benchmark of the tide gauge and a stable point in the port, which is a mandate for the maintenance technicians. And we will make use also of a new Copernicus product, which is the European Ground Motion Service, which provides spatial information of vertical land movement in Europe. And as I said before, we will also use altimetry data as provided by Copernicus, in this case, sea level anomaly. With respect to altimetry, one of the signals that we can see in altimetry data, and also in accordance to the literature, there is an acceleration on the rate of sea level rise in recent years. In fact, the WMO noted that the 2013 to 2022 rate of sea level rise was more than twice that recorded in the first decade of the satellite record. And this is what we can see if we go and select the nearby altimetry data near each tide gauge as extracted from Copernicus. We can see this increase in the trends in the period 2006-2023, also around the Spanish coasts, coming from altimetry data. This increase is higher, as you can see in the north, in the Bay of Biscay. Is smaller in the Canary Islands, for example. These data belong only to the 14 stations where we have 30 years of data. If we obtain the same trends for different periods only with the tide gauge data, we have more variability, more uncertainties in the data, but nevertheless, we still confirm that we have an acceleration also in relative sea level in the Bay of Biscay. As the altimetry provides. But however, we don't see this acceleration in other tide gauges, as you can see on the right plot, when comparing the two trends for different stations. So, in principle, we observe higher trends since 2006 in Galicia and the Bay of Biscay, and lower trends in the Canary Islands, South of Spain, and the Mediterranean coast. If we represent for specific ports the monthly mean sea levels from the tide gauge, relative sea level in the tide gauge, and the altimetry data near each tide gauge, sometimes we find that the trends are not the same. Of course, this is not strange. We are measuring different things, but this is the kind of results we want to analyze to understand why those differences appear. For example, here you can see that for Barcelona, Ibiza, and Valencia, the sea level trend observed by our tide gauges is significantly higher than the one provided by nearby altimetry. Is this vertical land movement? Is there any problem in the stations? Why the three stations are showing the same trend? This is the type of study we need to do to understand, to perform. If we go to the study that the equipment, the team in the University of La Rochelle has started with our GNSS data, they are focusing on all our tide gauges collocated with a GNSS, and also plus a nearby GNSS station which is closer to the tide gauge in a radius of 15 kilometers from the tide gauge. And they have selected these stations from the permanent GNSS station. As you can see in this chronogram, the amount of data we have is very limited. But we have already some time series that are very large. For example, we have a time series of 20 years, 19 to 20 years in Ibiza. But for most of the stations, we established these stations a few years ago. We only have 3 to 5 years of data. The best station is the one from La Coruña. The station belongs to Geographic Institute, where we have 25 years of GNSS data. The good thing is combining the collocated tide gauge with the collocated GNSS data with the nearby GNSS information is that we could extend back in time, if we have more data, these short time series that perhaps nowadays are very limited to obtain vertical land movement. If we represent the trends of the vertical land positions in all these stations, you can see that most of the GNSS stations reveal that there is subsidence in many ports. And then we should be able to estimate a vertical land movement trend that could be compared with the trend obtained from the tide gauge. But we need to identify if this is a real phenomenon or if we have any problems in the equipment, there has been any changes, and we come back now to the metadata problem. When we compare the trends between tide gauges, altimetry, and the GNSS, with all the limitations, at the first preliminary results, we see that there are some ports where we obtain a difference that is explained by vertical land movement. But this is not happening in all the ports, so we need to analyze and understand in more detail all the leveling campaigns of each individual tide gauge. And then we come with the use of the INSAR. The idea of INSAR is to obtain a spatial variation of this vertical land movement. Nowadays, this data from Copernicus have an uncertainty that is too large, is well above 1 millimeter per year. So the idea is to combine the GNSS information we have at the tide gauge with this new product in Copernicus in order to obtain the spatial variability of vertical land movement in the port and the nearby city, which we think could be interesting in the future. I will try to hurry up because I am going late. This is an example for La Gomera. In a wonderful way, in a wonderful world, we would have a linear trend. This is not that easy. We have some local movements. You can see here for the last period in La Gomera, the last year, there is some problem in the tide gauge. So we need this information for correcting our sea level data when we distribute the data. This is another example for La Coruña, where we have 3 different time series. Fortunately, we have a very old one, which is showing a very stable subsidence that can be used to derive this spatial variability for the Coruña and Langosteira ports. This is another example for Ibiza, I think, no, Barcelona. And so I conclude here. I just want to summarize that, we found that we have the highest value of annual mean sea level in record in 2023, and that we are really facing an acceleration of sea level rise. But we are very concerned about how to monitor these long-term trends of mean sea level evolution if we have the adequate network, the adequate instrumentation, and if we make use of the adequate data that is available publicly in Copernicus. This exercise is starting now, but is an example of combination of all this type of information to provide these additional details with uncertainties in the future. This is not yet ready. And also the idea is to become an operational product, which is also demanded, and let's see if we can do it. And to conclude, I would like just to say that we need further interaction with our port users. We need to understand their real needs And that's perhaps the most difficult and challenging work. We need to understand which is the level of risk you can accept, which is the level of detail, which is the uncertainty in sea level rise, which is critical for you. And that's it. Sorry for the delay. Thank you very much.
Thank you, Begonia. I'm not sure we have time for question or if something urgent. Okay, so we can move to the next presentation from Elena Terzic, and we will travel now in the South Adriatic Sea. Elena, if possible, 10 or 12 minutes for having the time for questions will be perfect. Thank you.
Where are the presentations? Sorry.
Okay. You have the slideshow on PDF? You have only the PDF? It's still the PDF. If you can, there to...
This lectura? This one? Modo lectura?
Primero hay que duplicar la pantalla.
Ah, bueno.
Okay. Hay que forzarle, a ver, un momentito. ¿Se ve?
No.
¿No?
Full screen on the right?
Pero primero hay que decirle. ¿Ahora sí? Vale. Ahora sí. Full.
Now I have even less time. Now I have even less time.
10 minutes.
Okay, then,
Okay.
No, I'm joking. Okay, so this presentation is actually a result of a joint collaboration between institutes in Croatia, Italy, and Slovenia. And it's focused on the Southern Adriatic Sea and its deepest parts. So the deep Southern Adriatic pit, which is highlighted in the pinkish hue. And as you will see throughout this presentation, is a region which is highly influenced by climate change. And to explain in more detail, so the major processes that are influencing the deep Southern Adriatic pit are the shelf generation, so the North Adriatic shelf generation of dense water, which occurs due to cold and dry bora wind. And additionally, we can have also open ocean convection generated in the Southern Adriatic. So this dense water, deep water flows, if you follow the yellow arrows, towards the south, out of the Adriatic Sea through the Taranto Strait, and then the compensating flow comes from the eastern Mediterranean Sea through the warmer and saltier Levantine intermediate water. So we wanted to observe what has been happening recently and putting that in a historical context. So for that reason, we gathered Argo data in the Southern Adriatic pit, which you can see are color-coded by time. We also got data from the stationary mooring managed by colleagues in OGS, which is the yellow star in the region. We additionally had CTD data since 1957, so a very long historical time series managed by the Institute of Oceanography in Split. And then, of course, because so the Southern Adriatic pit is influenced by processes in the Northern Adriatic and also to the Levantine intermediate water, we looked also at data in the north, so the Vida buoy managed by the Marine Biology Station in Piran. And we took Era 5 reanalysis data for turbulent heat fluxes, which are a proxy for Bora, so for dry cooling, and also Argo data from the North Ionian Sea. Okay, so those are the results since the beginning of measurements, potential temperature, practical salinity, and potential density anomaly. Basically, you can see CTD data in orange and green colors. You can see the mooring data in purple and Argo is in blue. I follow all these colors throughout the presentation. And just a few main pointers. What we can see is a strong decadal variability in terms of temperature, salinity. But since the mid-90s, for temperature, and since mid-2000s, we can see overall increasing trends. And in terms of density, we observe, well, it's difficult to see because the data set is quite scattered, but we have salinity-driven increase until mid-2000s, and now, since mid-2000s, we have a steady decrease, which means that density is predominantly temperature-driven. What we also observed is that during the dense water cascading events, so when the dense water enters the pit, we have a steady drop in the temperature, so starting from half of a degree in 80s to less than 0.2 degrees in 2012. And these things are further changing in the last decade, so this is a zoom in the last 12 years, and we can notice some very peculiar events occurring. So major cascading events of dense water occurred in 2012, 2017, 18, and 2022. I will mention this a bit later. But what we notice since 2017, actually, during this cascading event, you have a temperature increase for 0.2 degrees or 0.3 at greater depths, and an increase in salinity in 0.02. So, and also the trends between one and the other cascading event are actually accelerating. And this is even clearer. So this is the time series of Argo data throughout the entire water column for the Southern Adriatic pit. And in front, we put the mooring data at the deepest station, so at 1,200 meters. So what you can see here below, its density, you can see these cascading events. So again, in 2012, 2017, 18, and 2022. But we actually have also these huge temperature jumps during these cascading events. And also, to put in the context of the entire water column, for example, if you follow the 14-degree isotherm, which is yellow colored, 12 years ago it was less than 100 meters deep. No, sorry. Now we have near the bottom. And similarly for, say, 38.9 isohaline, which is again the yellow one, 10 years ago it was around 100 meters deep, and now it's at the bottom. So we see this really strong warming and salinification rates. So to put this in a wider context, so we have to see what's happening in the North Adriatic and also in the Ionian. First we look at the North Adriatic dense formation site. And for that reason, we took the turbulent heat fluxes, so the latent and the sensible heat fluxes, for winter months, so December, January, and February, and obtained anomalies by subtracting a baseline between 1980 and 2010. So what you can see is that until 2012, 2017, we actually have negative anomalies, which corresponds to the dense water cascading events. But since 2018, we have positive anomalies, so we cannot explain this dense water formation by cooling rates or, Bora cooling alone. For this reason, we took the data from the Vida Buoy in Piran in Slovenia, managed by the Marine Biology Station. And what we basically did, we checked the winter yearly maximum of potential density anomaly and looked at the corresponding temperature and salinities. And what we observed is that we have this paradigmatic shift, so going from low temperatures to now high salinities. So salinity is becoming the dominant forcing, it has the dominant forcing in creating dense water. And if we look, if we look further at trends, so this is from Argo data on top for the Southern Adriatic pit and in the bottom for the Northeastern Ionian, okay? And we calculated trends for the last 12 years, over a decade, 400-meter increments. Basically, what we can see in the Southern Adriatic pit, that we have increasing warming trends with depth, reaching up to 0.8 degrees per decade. And we have also largest salinity trends around the Levantine intermediate water, but also at greater depths. And oppositely, the potential density is actually decreasing with also negative trends. So what we observe that the density is decreasing, this is also seen from the trends. Can we explain this through a changing Levantine intermediate water intrusion? No. If you look at the trends in warming, they are 3 to 4 times lower. At depths, they are minimal, but you have up to 0.21 degrees per decade in terms of temperature, and half the trend in salinity. So we cannot explain these changes by the changes in the Levantine intermediate water, which means that local processes in Adriatic have also a major influence. So this morning in the talk it was mentioned that winters are becoming warmer and drier. This has a great impact, less precipitation, less river discharge. All of these things exacerbate actually the effect in the Southern Adriatic. Sorry, one slide back, I forgot to say here because I thought I was running out of time. Based on the profiles of Argo floats, we also calculated the changes in the stratification. So basically what we notice is that we have a decrease in temperature gradients up to 60%, which means, and we have a stratification decreasing throughout the entire water column, which then facilitates double diffusive processes. And yeah, that's all I had to say. Basically, those are the main conclusions. And I think I'm, yeah? Okay. Okay, that was it, yeah.
No, you was perfect, so we have time for questions. We have only 30 minutes late, so. Vanessa? You have a question for Elena? No, I'm part of the author, I cannot be, D'accordo.
Could you connect fluctuation in salinity on Pula buoy with Po River discharge?
Sorry, I didn't.
Could you connect salinity fluctuation on Pula buoy? Do you have buoy?
For the Po River?
Could you connect them? Fluctuation and salinity?
Yeah, we didn't use the data, but we could check.
We didn't connect them, we didn't use those data. But we know that but certainly for the different types of events, the lack of ribbon outflow or the lack of rains, a bit for more dry winters can affect certainly the whole Adriatic. Now this is affecting this rabbit. But we didn't connect it to the Po River, to those data. To precipitation, even though it's quite complicated to get it in the Adriatic, we will, so it's not there available. Okay. Christian. And then we will have today the last one we will finish today.
Thanks for the presentation. I'm not expert on the topic, but I still was on this cascading effect during the cold borer period. Is this also that the process changed? I mean, I was expecting more like pulses in the past, now that it's driven mostly by salinity. Is it a slower process?
You mean during cascading?
Yeah.
Do you want to answer? Yeah, if you want. Yes.
Yeah. What we have is cascading, we have gravity currents. There are pulses of gravity currents arriving. In the beginning, and there will be, there is a paper that will be submitted in a few weeks regarding this. And this is in the 2012 we have the temperature, it was a temperature-driven event. While on the 17, 18, and 22 was, it was a salinity-driven event. So the complexity is different. And also the maximum, if you have the maximum in Northern Adriatic, I think Ricardo presented the 2017 part of the event. We will have also the 18 and the 23. Everything is related when the maximum and the convection and you reach the maximum of salinity. And the maximum salinity then it is flowing as rain or as a gravity current to the southern Adriatic. So it is not really specific. What I can say about the timing is that before event was temperature driven, and now is salinity-driven events. The speed of the currents, we are presenting the speed of the currents that we calculated. We calculated for the, this is a travel between North Adriatic and the Bari Canyon when they are the CNR moorings, and then for the CNR, from CNR to the pit. The time for the most of the all event, we calculate the velocity almost the same from the southern, from the canyon to the pit. It maintained almost every, the time of travel to arrival is almost the same, changing for a couple of days in order. While instead the travel time from the north to the south has changed in some way.
So salinity, what's the mechanism of salinity impact? Is it preconditioning, evaporation, or precipitation?
But there's no precipitation. We have we have no Paul River discharge. Yeah.
No, I mean drought is what I mean. Also with precipitation.
Drought is one of the main issues in this. The precipitation is just very localized, and so we have the formation. Like in 2018 event, the maximum of if you count the maximum of the density was at the beginning of March. Okay, getting the maximum. That is very strange because you get mostly in February the maximum of density of the winter, but it was a very mild. It depends on the.
So it's a slower rise than if it was driven through Bora.
Each year is changing. It's not now because you have these stream events. They are changing. This is not really now as we expected. In a long time, that was a preconditioning. There was the convection period, post-convection period. Now the winter is changing.
Okay, Vanessa, yes, I think it's time to let the floor to...
I said to...
to Baptiste?
To Baptiste to come.
Hi.
Yeah.
Please, Baptiste.
He's worse than me. Okay.
Don't be afraid. So yes.
Do that quickly and...
No, do your best. So synergy with satellite, in situ measurement, models, everything to finish.
Yeah, and especially the... Especially the SWOT satellite, which is one of the focus, and it's good to have an opportunity to discuss a bit the first results about this new data. So, yeah, my name is Baptiste Moore, and I'm working at BIMEDEA, the Mediterranean Institute for Advanced Studies in Mallorca, in Spain. And so this is a result of a team of people here with the names, and in particular, I'd like to acknowledge the work from Elisabeth Verger, Miralles, Laura Gomez Navarro, that have looked into details on the data. So this is about the SWOT satellite. SWOT is it stands for Surface Water and Ocean Topography. It's a satellite that was launched December 2022 both by NASA and CNES spatial agencies. And so it's a family of altimeter satellites, and it has this new interferometric technology that allows to monitor not only under the track of the satellite, but over a swath, which is around 120 kilometers, so 60 kilometers both sides of the track.
So the other, what is new is that it monitors or it provides a two-dimensional view of the sea level variability, and also with high resolution. You know, we get resolution of 10 kilometers, which is much higher than what we had until now. So a bit the question in this workshop is that can it be a booster for the understanding of the small-scale circulation in the Mediterranean Sea and the associated impact on climate? So I'll try to give some answers about this. And so just to know, there was 2 different phases of sampling for the satellites. The first one was the fast sampling phase, the initial phase of calibration validation. So it's really, we have 3 months of fast sampling, daily repetitivity of the data. And in the Mediterranean, this is what you see here. You have 2 areas that were monitored, 4 tracks, 2 on the western basin, 2 on the eastern basin, with also some crossovers where you really have data every 2 times per day. So it's an opportunity to have insight of this daily variability and high resolution sea level. Then there is a science phase from July 2023, and this is covering the whole basin. We have tracks everywhere, but with a much lower time repetitivity. Every track comes back every 21 days. So with the crossover, it's about, I think, 11 days of really repetitivity of the data on a single position. So I'd like to discuss or comment what we had, the results we had in the FastWatt project. So we are dealing with the fast sampling phase, the first phase. So it's a project that is funded by the Spanish Ministry of Science of Innovation. And so it's led by Ananda Pascual and myself at IMEDEA. And we wanted with this to validate the SWOT observations. We want to integrate the observations with in-situ data and also high resolution modeling. And then we want to reconstruct the whole ocean fields to understand the 3D dynamics and of the small scale features. So for this, we organized an experiment at sea that was 2 campaigns. It was also part of the SWOT Adopt a Crossover Consortium, which is like a collection of in-situ campaigns that were done during the fast sampling phase worldwide. And so we wanted to go at sea and sample precisely small scale structures within the swath of the SWOT. Sorry. And so we were based in Palma, so you see the image, SST image at the time of availability of the ship, and we detected this eddy. There's no pointer, but you can see on the left hand, maybe here. Yeah? Okay, no problem. So there is this right here that was quite close to the harbor. We had a small ship, which is a research vessel SOSIB. And so we went there for in-situ sampling of the eddy and repetition of the sampling after a few days, 10 days, just to have an evolution of an idea of the evolution. Okay, here I add the stuff. Okay, so the 2 more details about the 2 campaigns. We had 2 legs, leg 1, leg 2. During leg 1, we really went to do cross eddy sections of the structure. We did that with several instruments. So we had 2 gliders first that went from south to north along the swath, and from surface to 700 meters. We had a moving vessel profiler to have high resolution data over the surface layer, ADCP, thermosalinograph. We also deployed 45 surface drifters and CTDs. And to complement this, we also had this high resolution data assimilative model, the WMOF model from SOSIB. And we also used this grid refinement that Maximo presented with 600-meter resolution. So these are a few plots from the model where we see that we had this kind of eddy present in the model. So this is the vorticity map on the bottom right. So you see this blue anticyclonic structure. This is a sea level elevation, and we had an idea with the model of the vertical structure of the eddy, which were also indicating how deep we had to sample. So we used that to go until 700 meters. Yes. So I show you results of the comparison of the SWOT with drifters and also SST here. SST is on the left. So you see we had a few 6 drifters that were trapped into the eddy. These are SBP drifters. So this matches quite well with the SST structure. And in the middle you have the SWOT contours and SWOT CC surface anomaly. So you also see that you have very good match for these, the location and the location of this small scale eddy. The core matches very well with the trajectory of the drifters. And you also see, if you compare with the conventional altimetry to the right, that you have much more level of detail, you have much more intensity of the surface elevation. And so you get refined view of what's happening. In particular, if you look also on the right swath, you have very fine structures that you don't have in the conventional altimetry. Conventional altimetry still have this eddy present, so it's not bad, but with a lower magnitude. And then this is the same kind of image, but the colors was changed. It was created by another person, but it's just to show the daily variability also that we have about this structure. So we see here 6 days of sea level anomalies, and you see how variable it is. So we see the contours. They are changing quite a lot during these 6 days. In particular, if you take day 25th. The structures, the core of the eddy is like more to the north, so we still have to see if this is a problem with the data or anything that can be dynamics. But yeah, still we see in what is new that we could not see before, that we really have this high variability at the daily time scale of the sea level. So now we can look at the depth structure, vertical structure, using the 2 gliders. So we have these 2 gliders going back and forth. They were separated by 24 hours, and so it's a total of 8 sections, a bit more than 3 days each. And this is an idea of the structure of salinity and temperature. We have this cold core, relatively fresh water, so it's typical of a Western Intermediate water eddy, and it is an eddy that is intrathermocline. It is a subsurface eddy. The core is subsurface. So SWOT is able to see this kind of the signature in sea level of this kind of eddy. And then with this glider section, we are able to compute the dynamic height by integrating the specific volume anomalies, and we compare this to the SWOT data. Okay? So the blue, because you have the section here in density, and the blue is the blue line thick is the glider dynamic height. So you see this elevation that corresponds to this anticyclonic eddy. You see also the magnitude is a few 2-3 centimeters, so it's not much, but it's still something. Significant signature, let's say. And we can see the match or the differences between SWOT and conventional altimetry here. Conventional altimetry, as we were seeing, is much flatter than what SWOT says. SWOT is in better agreement with the data. And if you see, then so the glider takes about 3 days to cross this section, and the SWOT, so we have 3 passes of the satellites during the 3 days. And the gray line here is what we represent. You see the daily variability in the SWOT data. And the black dots, black and blue dots, are the time when there is coincidence between the satellite pass and the glider position. So you see that for the 3 pass or 3 points, there's a very good agreement between the data. And so it seems that the daily variability also in SWOT is quite realistic, according to this. We also had comparison with the ADCP, so there we derive the velocities from the sea level anomalies, so it's small scale, but still we are here in the geostrophic framework, and we compare these velocities with ADCP, so here at 100-meter depth, so we just to remove the impact of the very surface where we have find quite large variability in the velocities. And again, we see that the intensity that we had in this eddy, which is represented by larger velocities, it's in much better agreement in the SWOT that it was in the conventional altimetry. So here again, an important improvement. And just to summarize, this is the RMSD results, comparison between dynamic height or velocities with ADCP, with glider ADCP and drifters. And so if you look at the green bar is the percentage of improvement, And you see that it is between 25 and 60% according to the data we are looking at. So to conclude, yes, it's based on this data, I think we have very promising capability of SWOT data to monitor the small-scale sea level anomalies with good accuracy, based on the comparison we have the multi-platform measurements. And yes, to answer to the question, that it should definitely contribute to boost the understanding we have of these small-scale features and all the associated processes that were commented by Nikos and Maximo about vertical velocities and others. So next also we will try to assimilate this data in the model or work more on the comparison with the model data, but still we haven't entered much into this. And just a final outreach material that we did, like the infography about how the approach of the FastSWOT project. There is also a nice documentary you can see on YouTube about these experiments, how they were done. There was a documentalist, a cameraman inside the expeditions, and acknowledgement of the partners and sponsors. And that's it. Thank you for your attention.
Baptiste, to finish this session, we can see if there are any questions. We are almost 1 hour late, meaning that I did a very bad job, Vanessa, but... So any question for Baptiste?
It's more than a question of curiosity, because I know that I was not so, I don't know too much about the SWOT, even though my colleagues were involved, Ricardo and Milena. But I know there was also an experiment from the French team also. So you focus more for your area, for the Balearic, but then you were not at the same time. I mean, they were at the same time. They were together with the experiment from the French. That was huge, but as I know.
Yeah, there were 2 other experiments by the French during the same 3-month period. The second one was in the same time that one, so we were coordinated. We had the idea of going together the same place, but at the end we went to different places, but close by. And so this is the sea SWOT. It was more Gulf of Lion, and then the bio SWOT. That is a bit more focused on the biological impacts. But all these, yeah, we still go together in the analysis of data and share quite a lot. And they also have very good results in terms of the SWOT capability.
Yeah, I've seen that. So it says, yeah, I think for analysis of data, it makes results and publication we have for the next 5 years or something. Yeah, I mean, there is a lot to get from those data.
There is the fast sampling was only 3 months.
Okay.
So yes, when with these dense in situ campaigns and fast sampling, I think there is a lot to get. There is this 3 month that you can also analyze, and then there is the other from July 2023. It's every 10 days, let's say, 11 days. So it's another way of analysis.
But you were, just a question, you were merged together with the French to extend the area, or will be always localized just in some parts of the Mediterranean?
It's localized. So you saw there are 2 swaths. So we went to let's say the left one, they went to the right one, to the right swath. But still we had to go to specific structures. We had to go to specific eddies or specific fronts. So it's not the same structure, but it has to do, it's still the same water, let's say.
Any other question? No? Okay, so it's time to relax now. I think we had a good session with a lot of discussion, a variety of topics. We can be proud of belonging to the observing community in the Mediterranean Sea. Yeah. And I know what you will say.
No.
That tomorrow start at 9 exactly, and we have to arrive at 8:30.
No, I am really tired to say this, because nobody listened to me. So.
But tomorrow it's at 9.
Tomorrow is at 9, and we will start with the modeling part. Now, I was also to thank all the speakers, because there were really nice presentations that provide very important information that maybe, as I said, part of the community didn't know. So thanks to all of you that present today, and thanks for coming and presenting. And see you tomorrow before 9 o'clock.